Hi, I'm Richard Nisbet. I teach psychology at the University of Michigan, and this course is called Critical Thinking for the Information Age. I've spent most of my career studying intelligence and reasoning, and I've learned a lot about how we reason and how we can do it better. So the course is intended to make you smarter. Well, you may wonder if you can make yourself smarter. A lot of people are inclined to think that you have whatever intelligence you were intended to have, but that's not true. You've been getting smarter all your life. School has made you smarter. Your family has made you smarter. Your friends, the media, and you've been making yourself smarter because you have good rules of inference that allow you to learn about the world. As it happens, humans as a group have been getting smarter over the past few hundred years. This is because the industrial age required some new skills of people, namely the 3 R's. People had to do reading, writing, and arithmetic in order to hold those jobs that were coming available. For free, learning those things, people improved their ability to think logically, improved their ability to think in hypothetical terms, and improved their ability to think about abstractions. The more you have of these kinds of skills, the better equipped you are to function in industrial age jobs. These are the kinds of thinking skills, by the way, that IQ tests measure. And the more complex the job, the more necessary those IQ type skills are. We keep on getting better, actually. It didn't just start a long time ago, it continues. Over the last 80 or 90 years, people in the advanced economies have gained more than 20 points in IQ, which is really huge. But we live in a new era, which some people call the information age. The IQ type skills, general intelligence, aren't enough for the information age. You need specific tools for dealing with data, how to collect data, how to analyze the validity of data, how to find patterns in data, and equally important, how to avoid seeing patterns that aren't there, how to critique arguments based on data, including especially arguments that you encounter in the media based on poor data or poor inferences made from those data. And you need also to have the rules for making decisions based on data collected by someone else. This is not just for professional purposes, although I'm pretty sure that most people who are watching this video will be using some of those tools in their professional lives. But in the world we live in today, they're essential for being able to make sensible judgments and reasonable decisions. The needed skills here come from statistics, probability theory, scientific methodology, cost-benefit analysis, and cognitive psychology. I hasten to say, if you're math phobic, don't worry. If you passed arithmetic in the 4th grade, you're prepared. The most complicated math operation you would be asked to do here is division. In fact, even if you've never had a course in any of these fields, you already have a lot of the necessary skills. You've been doing statistics all your life, for example. If 3 friends recommend movie A and 1 friend recommends movie B, you're probably going to go to movie A, and that's because you have an intuitive understanding of the law of large numbers. More evidence is better than less evidence, so odds are you're going to like movie A better than movie B. You've also been making probability estimates all your life. What are the odds that the University of Michigan football team will beat the Ohio State University football team this year? What's the likelihood that you'll get a job that you've applied for? You know a lot about scientific methodology, what constitutes a good experiment. Even babies do, as a matter of fact. We used to think that babies do nothing but eat and sleep and lie around being cute, but actually they're making inferences about the world constantly, using, in some cases, some pretty good rules about it from experimental science. The same is true for cost-benefit analysis. You've been making cost-benefit decisions all your life. Shall I do this or that? This involves certain costs and gets certain benefits. That involves other costs and gets other benefits. But you can do cost-benefit analysis more efficiently than you do now. You can do all of these things, in fact, a lot better than you do, and it isn't hard to learn. The tools are unusual because they'll continue to get more powerful over time. Avogadro's law isn't going to stick with you because you almost certainly don't use it, but even if you did, it would never be a more powerful tool than it was when you learned it. It's going to be used for the same things, limited things. But every time you use the law of large numbers, your ability to use it will increase. You've probably heard the expression, use a new vocabulary word twice and it's yours. In this course, it's use a new concept twice and you'll use it 4 more times in short order. This is going to be the least effortful learning you've had for a while. The stuff is easy to learn, it's hard to forget, and it's impossible to not use. You're going to be using these principles automatically. They're just going to push out intuitive principles which are suboptimal for thinking. I'll give a quick overview now of the course. The first lesson is on statistics. The concepts we'll take up are variable, normal distribution, standard deviation, correlation, reliability, and validity. If you've had one course in statistics, spend a few minutes looking at this material in this lesson to see if it's helpful. I think it will be. If you've had several courses in statistics, it makes sense to go straight to lesson 2. And there's no math, remember. Let me say that more emphatically. There's no math, so don't worry about that. Lesson 2 is on the law of large numbers. This states that sample values resemble population values as a function of their size. So your judgment about Bill's honesty or the quality of food in the new restaurant becomes more accurate the more evidence you have. This is especially true when there's a lot of error in your sample, and we're not very well calibrated with respect to how much error there is for various kinds of judgments. The big problem to be overcome in knowing when and how to use the law of large numbers is recognizing that there is error and having some estimate about how big it is. Lesson 3 is on correlation. Correlation tells us the degree of association between 2 variables. Correlation between mother's height and daughter's height, between IQ and income. It's difficult to detect some correlations, and worse, we detect lots of correlations that aren't really there. And there are ways to avoid that. And finally, you need protection from the media because many reporters don't understand some of the most basic principles about correlations. Lesson 4 is on experiments. What makes a good experiment? Why experiments are superior to correlational evidence? The concept of natural experiments. In the 1950s, there used to be ads on TV about the town without toothache. And they actually had, and it was Crest, as a matter of fact, who used to run those ads, and it had been discovered that there were 2 towns very close to one another, which were identical in every way, about the same size, people had similar occupations, etc. But one of them just happened to have a lot of the chemical fluoride in the water. And those people had fewer toothaches. So as a consequence, Crest and almost all other toothpaste have fluorides, and the drinking water in a lot of cities has fluoride. You'll learn something about how to do experiments on yourself. Does coffee make you more or less efficient, for example? Or does it just make you jittery and unpleasant? And then we'll talk about the terrific costs that society pays for the experiments that it doesn't do. Lesson 5 is on predicting. One of the most important concepts there is the concept of regression to the mean. The basic idea here is that extreme values for any given variable are rare. And so the next value that you encounter, if you see a rare extreme variable, is probably going to be less extreme. Joan is probably not going to be as extraordinarily generous the next time you see her as she was this time. And you'll be learning about how to use the concept of base rate. Predictions about a case should take into account what other similar cases are like. We shouldn't just pay attention to the information we have about the particular case in question. What are other cases like? Lesson 6 is on cognitive biases, how we make errors in judgment because we lack certain important concepts. One of the very oldest concepts that we'll be talking about is the illusion of objectivity. This concept is at least 2,500 years old. We tend to think that when we see something, when we listen to something, that we're understanding it in some direct, automatic way. And in fact, everything, even the simplest visual perception, we have by virtue of a lot of overlay of perceptual and cognitive processes. We'll be talking about something called the fundamental attribution error. We tend to automatically think that the behavior of objects and people is somehow produced by something internal to that object or that person, abilities or traits, when in fact often the place to look is the situation that the person is in. That's the real cause of behavior. We'll be talking about heuristics, which are rules of thumb that are pretty good most of the time, but can lead us astray when we're assessing probability and causality. And we'll be talking about confirmation bias. When we test hypotheses, we tend to look only for evidence that would be supportive and not for equally valuable evidence that might be contradictory. The next lesson, 7, is on choosing and deciding. We'll talk about how to carry out a cost-benefit analysis and when to ignore the results of a cost-benefit analysis. And we'll talk about the concept of opportunity costs, which is how to avoid taking actions that make potentially more valuable actions impossible. And we'll talk about sunk costs, how to avoid carrying out an action for no better reason than that you paid to do it. You'll be learning that economists are a different species. They don't eat lousy food just because they paid a lot for it. You'll be finding that that's a useful lesson for yourself, I'm pretty sure. The last lecture, before the wrap-up, is on logic and dialectical reasoning. We'll take up two aspects of logic. One is syllogisms. All men are mortal. Socrates is a man, therefore Socrates is mortal. Has to do with categories and quantities, some, all, none, so on. And the other is conditional reasoning, which is much more powerful set of reasoning skills, where the conditional is if P, then Q, and that's the fundamental aspect of conditional reasoning. If P is the case, then Q is the case. You know that P is the case, therefore you know that Q is the case. And if Q is not the case, you know that P is also not the case. The next part of that lecture has to do with what's been called dialectical reasoning. And there, instead of trying to find an answer to a problem which is logically compelled, you're looking to find the truth about some matter. For example, if you have two propositions that seem to be contradictory, in the logical approach, you want to get rid of one of those, decide which is correct. In a dialectical approach, you may be much more interested in finding out in what ways both propositions might be correct, or in what way you can understand the world better by virtue of thinking simultaneously about those two propositions. There's a text for the course called Mindware, Tools for Smart Thinking. I wrote the book. It's available in paperback, Kindle, and audio. Let me emphasize that you don't have to read the text in order to appreciate this course. Every lesson is intact in and of itself, and it doesn't require additional material. But if you're interested in seeing more in-depth material for the course, then you may want to look at that text. The book talks about the concepts in this course and lots of other concepts as well, concepts from logic, from dialectical reasoning, and from philosophical analysis and philosophy of science, and so on. So each lesson will be accompanied by an assignment from that text. I hope you enjoy the course, and I hope you enjoy the text, and I'll see you soon. Hi, I'm Richard Nisbet, and this course is Critical Thinking for the Information Age, and this is Lesson 1. It's on statistics. We'll be talking about some basic statistical concepts that are fundamental to the course and essential for everyday life. If you've had no statistics or just one course, I think you'll get a lot from this video. If you've had several courses, you may want to watch for a couple of minutes and see if it seems worthwhile. Otherwise, go straight to Lesson 2. In a standard introductory statistics course in college, you'd spend 95% of the time on definitions and formulas and calculations, and maybe 5% of the time on examples. This whirlwind tour you're about to take is the reverse. It's light on definitions and heavy on examples. First concept is the concept of a variable. A variable is something that varies, as opposed to a constant. The current temperature is a value for the variable temperature, 27, 30, 19, 29, as opposed to freezing temperature, which is constant. It's always the same. Some variables would be height. Some people are taller than others. IQ. Some people have higher IQs than others. The number of eggs laid by Farmer Jones' hen house each week, and the number of errors per week in the manufacture of Ford transmissions. Anything that varies about a thing, event, or person can be a variable. Variables are distributed in some way. One of the ways they're most frequently distributed is the normal distribution pattern. It's called the normal distribution because it's so common. It's also sometimes called the bell curve because it looks like a bell. In this kind of distribution, the mean is the most common value, and that's in the middle. As you get further and further away from the mean, cases become rarer and rarer. So let's create a distribution. How about the distribution of cooking ability? Think of somebody who's a really good cook. That might be your grandma. Think of somebody who's not such a good cook, maybe your roommate or your cousin, somebody who has trouble with the grilled cheese sandwiches, and then somebody who's at the mean is the average Joe. And there's lots of average Joes compared to good old grandma's cooking and your poor roommate's cooking. Cases become fewer and fewer as you get further from the mean. An important point about the normal distribution, you can describe it in terms of standard deviations from the mean. That's almost like the average deviation, but not quite. The mean for the number of eggs laid by Farmer Jones' hens each week is 6, let's say. Hen number 28 laid 8 eggs last week, so the deviation there from the mean is 2. And hen number 17 laid 5 eggs last week, so the deviation there is -1, that's 5 minus 6. And the average deviation is the absolute value of 2 plus the absolute value of -1 divided by 2, which is 3, divided by 2, which is 1.5. Okay, so let's look at the rendering of the normal distribution, which has standard deviations indicated. And let's think about a particular kind of distribution. Let's take the distribution of heights of American males. The average American male is a little less than 5'10", and the average deviation is a little less than 3 inches, and so is the standard deviation. So here's the mean, here's -1 standard deviation, here's +1 standard deviation. Now, standard deviation fact number 1 is that 68% of all cases, eggs laid per week, transmission errors per day, male heights, are within -1 standard deviation and +1 standard deviation. So slightly more than 2/3 of all American males are between 5'7" and 6'1". Standard deviation fact number 2 is that 84% of all cases are between the bottom of the distribution, -4 or 5 standard deviations, where there are almost no cases, up to 1 standard deviation. There you find 84% of cases. So 84% of all males are less than 6'1". And about 16% of American males are taller than 6'1". Standard deviation fact number 3 is that 96% of all cases lie between -2 standard deviations and +2 standard deviations. So 96% of all American males are taller than 5'4" and shorter than 6'4". Standard deviation fact number 4 is that you can convert standard deviations to percentiles. The mean is always at the 50th percentile. 1 standard deviation is always at the 84th percentile. And 83% of cases are below the 84th percentile. And 16% of cases are above the 84th percentile. So IQ scores are represented in terms of standard deviation from the mean. The mean is arbitrarily defined as 100. So if the average score on that IQ test was 223 questions gotten right, we say the average is 100. And that's also what we say if the number of questions gotten right on average was 43, or if it was 767. It's just the convention. We know 100 corresponds to the average score. The standard deviation is arbitrarily defined as 15. That means we know that about 2/3 of people have IQs between 85 and 115. We know that a person with an IQ of 115 is about at the 84th percentile. And we know that a person with an IQ of 130 is about at the 98th percentile. So a person with an IQ of 130 is higher than 97% of the population, the same as 1%, and lower than 2%. Standard deviations are useful for thinking about all kinds of things. For example, finance. Imagine you're considering a stock with a 4% average per year return over the last few years and an average standard deviation of 3%. If the future is like the past, and if I were your financial advisor, I would tell you right now that past performance is no guarantee of future performance. But if it were to be, you could assume the following. So let's look at the normal distribution of these gains. The mean is 4%, and the standard deviation is 3. So 1 standard deviation above the mean is going to be 7, and 1 standard deviation below the mean is going to be 1. And we know that 68% of all cases are going to be between 1 and 7% gains. We also know that about 16% of the time, gains are going to be greater than 7%, and about 16% of the time, gains are going to be less than 1%. That's pretty stable. But if the standard deviation is 12, we get this kind of pattern. We find that 68% of the time, the gains are going to be between -8% and +16%. And we know that 16% of the time, gains are going to be more than 16%, and 16% of the time, they're going to be worse than -8%. That's pretty volatile. So what are the implications for buying stock? if you know the standard deviation, you have some pretty precise numbers to think about. If you're not counting on the stock for current income, why not go for volatility and buy the high standard deviation stock? In the long run, you'll probably make more money. On the other hand, if you're counting on income from the stock for the next few years, or if there's a possibility you may have to sell that stock for ready cash, you may want the low standard deviation stock because that's more stable. You're not going to lose your shirt, although you're not going to get rich either. Standard deviations are also very useful for thinking about effect size. The effect size is the magnitude of difference in standard deviation terms. There are other ways of calculating it too, but the most common way to calculate effect size is in standard deviation terms. So the effect size is what is the difference between one condition and another. For example, imagine you've designed a new way of teaching algebra. Kids taught by the old method get 72 on the exam, and kids taught by the new method get 78 on the exam. Is that a big deal or not? It completely depends on the standard deviation. So the mean is 72. If the standard deviation is 6, that's 78. That's a big gain because that takes the average kid from the 50th percentile to about the 84th percentile, which is no joke. On the other hand, assume that the standard deviation is 18. If so, it's not such a big deal because the gain is only 1/3 of a standard deviation, which is the equivalent of going from the 50th percentile to just the 64th percentile, which is not such a big deal. And you might want to take into consideration whether there are added costs if that's all the gain you're getting. Notice that many journalists don't understand that raw means are not very informative. It would be pretty common for a journalist to say, well, the old technique allowed students to get on average about 72 problems right. The new technique allowed about 78. The difference between 78 and 72 is 6. So 6 divided by 72 is 8.3%. So students got 8% better. That's literally meaningless because you don't know how big an effect is unless you have a sensible metric. And the standard deviation gives you the metric. It tells you that 78 is worth moving 34 percentiles up from average. To give percentages in a case like this is almost as meaningless as to say that the new Star Wars movie was 8% better than the new Batman movie. So that's what we've done today for a single variable. In the next session, we'll be talking about two variables at the same time, namely correlation. So in this segment, we're going to be talking about correlation. Correlation measures the association between variables. To give some examples, let's start with cooking ability, which we dealt with in the previous section. And we're going to relate that to age. And we already know 2 points here. Your roommate is young and is not a very good cook. And grandma is old and she's a great cook. And if you were to collect additional data, you'd find a tendency for people who are not such great cooks, not maybe as bad as your roommate, but not terrific, are going to be youngish, and people who are better than the average Joe are going to be relatively older. And that gives us the correlation, which is indicated by the diagonal here. I'd like to give you some examples of correlations of various magnitudes. Correlations range between -1 and +1. A -1 correlation means that there is a perfect correlation such that the higher you go on the x variable on the bottom, the lower you go on the y variable. At the other end, a correlation of +1.0 indicates that the higher you go on the variable x, the higher you go on the variable y. In between, you have what would be considered a very modest correlation of 0.3. and zero point 0.5 would be considered moderately high correlation. Notice that with the 0.3 correlation, it's very hard to see from this so-called scatter plot because you're scattering these dots across this figure. It's hard to see that there's actually a relationship there. With correlation of 0.5, it's easier to see that there's a correlation. And with a correlation of 0.8, it's totally obvious that there's a substantial correlation. Correlations of 0.5 are considered moderate. Correlations of 0.7 or higher are considered strong, although this varies from field to field and problem to problem. This is a rough way to calculate degree of association. So I'm going to give you examples of some correlations that you encounter in your life. The correlation with SAT scores with college GPA is about 0.4. The correlation between the heights of mothers and the heights of their daughters is about 0.5. The correlation between the heights of individuals with their weights, what would you think that should be? Pretty high, right? Because in general, taller people are heavier, but that's not a perfect relationship. And in fact, the correlation is about 0.7. The degree of overweight with the degree of cardiovascular illness, that correlation is about 0.3. And the correlation between blood pressure and cardiovascular illness is about 0.3. Those are very modest correlations, but they're big enough because you care a lot about the variable of cardiovascular illness. It's enough to do something about. Or you can correlate the height of basketball players with the points scored for the season. I don't know what that would be. You could correlate the average temperature in the Rocky Mountains on a given summer day with the number of forest fires that day, and so on. You can correlate almost any variable with almost any other variable. There are two basic ways of looking at correlations. One is a rank order correlation. You put one variable on one side, so mother's height, ranging from rank 1, the shortest, to rank 10, and then you note that the shortest mother has a daughter who really has kind of a middling height. The next shortest mother has a daughter who's very short. Here's a sort of short mother with a sort of short daughter, and so on. And when you perform the computations here, you find that the rank order correlation is about 0.54. You can also calculate correlations by looking at the actual numbers in question. So this is height in centimeters, where again you see the shortest mother has a middling height daughter, the next shortest has a very short daughter, and so on. And this also gives you a correlation, which is about 0.5. The very first correlation, by the way, that we've come to know about in history is by Pearson, who invented the Pearson product moment correlation, which is what I just showed you an example of. And he had 1,000 cases where he had measured fathers' heights and sons' heights. And this is the scatter plot you get. This is the distribution. Notice that things are very dense, many, many points right here toward the middle of both distributions. That reflects the fact that these are both normally distributed, so you're going to get the greatest density there in what corresponds to the middle of the two distributions. And even though you get a substantial concentration there and substantial degree of association, you can still get events like this very tall father has a totally average height son, and this very tall son has a totally average height father. Correlations are the way we assess reliability of measures. There's two different ways to define reliability. One is it's the degree to which a measure of a particular variable gives the same value across occasions, or the degree to which a measure correlates with itself. So, as an example, you could have the correlation between measures of height taken on different occasions, and you would expect that correlation, that is to say, the reliability, to be about 1.0. That's if you're measuring to a tolerance of a half inch. If you're measuring to a tolerance of a micron, you're going to have terrible reliability because the person took a slightly deeper breath this time than last time, and that gets a different number. The correlation between SAT math score obtained on 2 different occasions is about 0.85. So the SAT people, when they tell you that you're probably going to get a very similar score if you take the test a second time, they're right. On the other hand, there's lots of wiggle room there, and some people who do not so great the first time around do a lot better the second, and vice versa. Or we can look at the correlation between Dr. Jones's judgment about whether your tooth needs filling on Monday with Dr. Jones' judgment on Thursday, that is across 2 different occasions. You might think that that's close to 1.0, but it's not. It's 0.8. Too bad you went to Dr. Jones on Monday and you got your tooth filled, but if you had waited till Thursday, she might have made a different judgment. A second kind of reliability is the degree to which 2 different measures, which are supposed to measure the same thing, actually give the same result. So, the degree to which 2 different measures seem to be measuring the same thing. I can give some examples. Correlation between IQ test A and IQ test B. If it's low, we know that at least one of them is unreliable. But in fact, tests that call themselves IQ tests tend to correlate in the range of 0.8 to 0.9. They're quite reliable. The correlation between dentist Jones' judgment about whether a tooth needs filling and dentist Smith's judgment is about 0.7. They're reliable, but they're not perfectly reliable by any means. Less reliable than a person is with himself or herself. Think about what you might expect the correlation to be between 2 reviewers' ratings of solid-state physics proposal submitted to the National Science Foundation. Well, boy, that's really hard science, and you might think that surely there would be very strong correlation. Actually, there isn't. The correlation is about 0.3. And the correlation for judgments of psychology proposals is even less than that. This seems surprising because we don't necessarily recognize that we're not looking at the full range of solid-state physics proposals. Like Joe, where we say, who's never taken solid-state physics, say, so propose something here. So we don't have that kind of range from perfectly terrible to terrific. We've confined the range to be reasonable to terrific. And when you have a narrower range like that, you're going to get a relatively low correlation. And this is something we'll be taking up again in the next lesson on the law of large numbers, because you need to pay attention to the reliability of any kind of subjective measurement that you have, even though it's a subjective measurement of something that's really very objective in some sense. Or we could see how reliable 2 sorority sisters are, or a judgment, for example, of shyness. That happens to be about 0.65. So sorority sisters are pretty darn reliable for judgments of shyness. More reliable, incidentally, than they are for judgments of physical attractiveness. Correlations also are the way that we measure validity of measures. Validity is the degree to which a variable measures what it's supposed to. For example, IQ with school performance, with occupational attainment, with income, all of these things are measures of intelligence. Not perfectly. There's a lot that goes into school performance other than just intelligence, a lot that goes with occupational attainment and income other than just intelligence. But if you didn't get a correlation between an IQ test with these things, you'd say, gee, I don't think that's a measure of intelligence at all. And in fact, all of those correlations run about 0.4 to 0.5. So they have some real validity defined in that way. Or we could look at the validity of a paper and pencil test of extroversion, how outgoing someone is, with ratings of extroversion of the same people across a number of situations. So we follow them around a party, a classroom, a committee meeting, and we see how outgoing they seem to be, and we give them a rating across all those situations, and we correlate that with the paper and pencil test of extroversion. I love loud parties, or I like nothing better than curling up with a book. And what you find is those correlations tend to run about 0.7. So personality traits can be measured quite reliably. However, and this is to steal a march on the next lesson, if you were to correlate that paper and pencil test of extroversion, that score, with the ratings of extroversion in a single situation, you'd get a number more like 0.15 or 0.2. So you can't get terribly good prediction about people along personality trait lines by virtue of having only a single score. Or we could look at Rorschach ratings of paranoia with psychiatric ratings of paranoia. There's a Rorschach test, it's an ink blot, and so somebody might say, oh, that's a very scary thing there, the eyes creep me out, and maybe that person is paranoid. But the actual correlation between judgments of paranoia by the Rorschach or judgments of anything else by the Rorschach is about 0. The Rorschach test has no validity. And there's a moral to that story, which is that for decades, people were given Rorschach tests by psychologists and psychiatrists, and there was no validity at all. Millions of dollars were spent and hundreds of thousands of hours of people's time was wasted, and wrong conclusions about them were drawn because no one ever took the trouble to see how valid these tests were. There are two very important points I want to make about the relationship between validity and reliability. The first point is that there can be no validity if there is no reliability. If your measure gives you a different score every time, and they're more or less random, so that Joe gets a high score on one measurement and a low score on another, and Tom gets a high score on one and a low score on the other, and there's no relationship at all, then you can't have any validity for that measure. There has to be some stability, some degree of getting the same answer twice before you can have any validity for that measure at all. A friend of mine, for example, found out that he has mold in his apartment. The question is, how much mold is there in the apartment? That sounds like a straightforward question, but it turns out that mold varies from moment to moment. I mean, now there's a lot of mold in the spores in the air in the corner, and 15 minutes later, there isn't much there. The measures that we have of mold are not very reliable, and therefore they can't be very valid. A second point is that reliability implies very little about validity. Now, if reliability is 0, there can't be any validity. But at the other extreme, reliability can be absolutely perfect, but there may be no validity. And we have a case study of that in the Rorschach. People learned how to score Rorschach tests from first Mr. Rorschach, Dr. Rorschach, started teaching people how to do it, and they taught their students, and their students taught students, and they all were doing it the same way. It's just that there was no relationship to reality of these various measures that they had. So we've been talking about correlations, and correlation is one of the main ways that science gets done. Next time, we'll be discussing an extremely important principle of probability, namely the law of large numbers. And that's an important concept to have in knowing whether we can trust our judgment based on the amount of evidence that we have about some matter. The course is Critical Thinking for the Information Age. I'm Richard Nisbet. This is Lesson 2, The Law of Large Numbers. This lesson deals with a reasoning principle that you've used all your life, namely the law of large numbers. But you don't use it as much as you should. So I want to start with a simple question. I'll tell you that there's a city with 2 hospitals, one with about 15 births per day and one with about 45 births per day. Now, as you know, there are about 50% of babies born who are boys and 50% who are girls. But which of these hospitals do you think has more days when 60% or more of the babies born are boys? The hospital with 15 births per day or the hospital with 45 births per day? I'll let you think about that for just a minute. I'll tell you that most people think there would be no difference, that there would be the same number of days in a year at the 15 birth per day hospital and the 45 birth per day hospital when 60% or more of the babies born are boys. Well, let's do a simulation. This is the hospital with 15 births per day. Okay, so there's our 15 births. There's 9 boys and 6 girls, so that's 60% boys. Does that seem at all unusual? Well, no, not really. As a matter of fact, if one of those boy babies were a girl baby, it would be 8 boys and 7 girls, and you can't come any closer to 50-50 than that. So it's not at all unusual. Now let's do a simulation of the babies born at the hospital with 45 births per day. Well, that's 27 boys born and 18 girls born. That's 60% boys. Does this seem unusual to you? Does this seem weirdly too many boys? Well, it should. Suppose somebody said, let's do some coin flips for money, a buck each. If it comes up heads, my coin, then I win that trial. If it comes up tails, you win. And then this were the distribution, 27 heads and 18 tails. You probably would feel you'd been taken for a ride. So it is, in fact, an unusual pattern to get. Given that we know that there's a 50-50 ratio of boys and girls, you can ask how likely would it be that you were drawing from that kind of distribution, a 50-50 distribution, if you got 27 boys and 18 girls? And the answer is that's only going to happen 3 in 100 times. It could happen, but it's pretty darned unlikely. Now let's look at a simulation for 450 babies. That's about the number of babies born in the state of Michigan on a given day. I assume that seems very, very strange to you, to have such a remarkable number of boys and such a remarkably small number of girls. But in fact, it's 60% again. It's 270 boys and 180 girls. So it's that 60% figure. How likely is it that you could get a pattern like this, given that the true proportion is 50-50? The answer is you could get something this extreme not even one time in a million. Now, what's going on here? The principle that we use to understand this is the law of large numbers, which says that sample values, for example, proportions, resemble population values as a function of their size. The larger the sample, the less likely it is that you'll get a fluke, a very unrepresentative value. So 60% is a very unrepresentative value for 50%, which is close to the true value. But it's common to get that kind of difference with a small sample. If the sample gets large enough, it becomes virtually impossible. The other kinds of population values for which the law of large numbers holds is mean, median, standard deviation, anything that you can use to describe a sample and to describe a population is going to get more accurate the larger the sample. So you're going to get 60% or more boys at a hospital with 15 births every few days. You'll get 60% or more boys at a hospital with 45 births, maybe 9 or 10 times a year. And for the state of Michigan, you'll get a day when 60% of the babies born are boys, precisely never. Suppose I told you I knew an executive who needed to hire a manager. He interviewed a man with got a great record, terrific recommendations from his previous employers. But in the interview, the fellow didn't have much interesting to say about my friend's company, seemed to have low energy. So my friend told his colleagues that the guy shouldn't be pursued. Just isn't for us, doesn't cut it. That sounds like the kind of thing that happens all the time, right? But is the executive's judgment really a reasonable one? To help you think about that, suppose I told you I know a soccer coach. For the non-Americans, I'll point out that that's the game you call football. So this coach is looking for a striker, and he goes to a practice for a high school kid who has a great scoring record and terrific reviews from his coaches. But at this practice, the guy misses some easy points and he just doesn't seem in control of the ball. So my friend tells his colleagues that the kid shouldn't be pursued, he just hasn't got it. Now, is the coach's judgment reasonable or not? People who know sports are quite likely to say, no, that's really not so reasonable. One practice, it's just not that much evidence. There's lots of variability. I mean, you can have an off day and look much worse than usual, or everything can be hitting on all 8 cylinders, and you can look much better than usual. And this kind of variability is captured in an expression like, on any given Sunday, any team in the National Football League can defeat any other team in the National Football League. So let's go back to my friend, the executive. Do you still think he's reasonable? Well, the 30-minute unstructured interview is not that much evidence. In fact, people have looked at how well you can predict performance in college, medical school, Peace Corps, Army Officer Training School, and many, many businesses and professions to see how well that interview rating predicts performance. And the correlation almost never exceeds 0.10. That's very, very small. That's equivalent to increasing the likelihood of hiring the better of 2 candidates from 50-50, which is what you would get if you were going to flip a coin to make the decision, to a 53% chance. Hardly seems worth the effort. If you have past performance and other judgments by other people, you can do quite well in predicting these same kinds of performance that I just mentioned. In fact, if you weight things properly that are in the folder, you can raise the chances of picking the right person to 65% or 75%. So this is the principle of the law of large numbers, again, but I'm going to modify it slightly for these purposes to say that sample values for events having a chance component resemble the population values for those events as a function of their size. In fact, the law of large numbers only applies where there is some kind of a chance component. There's no chance component to your measurement of how far it is between London and Paris, and the law of large numbers is irrelevant there. One measurement will do you. But sports are very variable. We know that performance can be much higher or much lower on any given occasion. But most people never observe all that many interviews, and you don't get to see how well the prediction from the interview corresponds to the performance of the person on the job. The truth is, the employer's judgment is even worse than the coach's judgment because interviews are not a sample of job performance. or school performance. They're a sample of interview performance. My daughter used to be an opera singer, and she told me that auditions and performances require different skills. Interviews and performance on the job require different skills. So the law of large numbers applies to all kinds of events in everyday life. We apply the law of large numbers when we see the variability, the error, but not for events that are just as important where we don't. The principle here is if your variable is human behavior, assume there is error variance and adjust your judgment accordingly. Suppose I tell you I have the basketball records for all members of a college team for a particular year. And I do, in fact. It's for the University of Michigan. And suppose I pick the names of 2 players out of a hat. Here we go. I picked up Andre and Bob. Now suppose I ask you the likelihood that Andre scores more points than Bob in the second game in the season, given that he scored more points than Bob in the first game. You're probably going to say it's greater than 50% and less than 100%. But just what probability would you pick? Now suppose I ask you the probability that Andre will score more points than Bob in the last 20 games of the year, given that he scored more points than Bob in the first 20 games of the year. What would you guess? First, the probability that Andre scores more than Bob the next game, given that he did this game. I've asked University of Michigan students to make a guess about this, and what they guess is that it's about 0.66. That is, 2 times out of 3, Andre's going to score more than Bob in game 2, given that he scored more in game 1. What's the actual probability? It's actually 0.68. So people are very well calibrated for basketball. And incidentally, they're equally well calibrated for spelling tests. I happen to have the spelling test scores for a whole year of a bunch of 5th graders, and the numbers are really very similar. So what is people's guess about how likely it is that Andre will have a higher total for the next 20 games, given that Andre had a higher total for the last 20 games? That guess is 0.77, the University of Michigan students estimate. So it goes from, in their view, a 2/3 chance to a 3/4 chance. The actual gain, however, is huge. It goes from about 0.68 to about 0.90. So people are well calibrated for both basketball and spelling, and for abilities in general, I happen to know, for one occasion to another occasion. And they recognize that you have a better chance if you're looking at 20 occasions versus 20 occasions, but they very substantially underestimate the gain due to the law of large numbers. Let's look at personality traits. I happen to know how friendly people seemed to be to raters, psychologists who were rating people in a wide range of situations. And I also know about the honesty of kids who were tested over many, many different kinds of honesty tests. Does the kid cheat in a game? Does the kid take more than his or her fair share of cookies? So, given that Alice was friendlier than Betty, on average, over the last 20 occasions, what's the likelihood that she'll be friendlier than Betty on average on the next 20 occasions? University of Michigan students guessed that that was about 0.83, and in fact, it's 0.82. So they got that right. What do they guess about the likelihood that Alice will be friendlier than Betty the next time she's encountered, given that she was friendlier than Betty the last time she was encountered? University of Michigan students guess that that probability is 0.80. Now, that's pretty suspicious, isn't it? They think that you can predict one occasion from another occasion about as well as you can predict 20 occasions, the average of 20 occasions, from another 20 occasions. In fact, it's remarkably far off. The actual probability here is about 0.55. In other words, it's just not very likely. It's slightly more likely than 50%, but it's not very likely that Alice is going to be friendlier next time, given that she was friendlier this time. So we wildly overestimate the stability of behavior from one occasion to another. Moreover, we have very little recognition of the role of the law of large numbers, which tells us that we would have much greater predictability for the average of 20 occasions from the average of 20 other occasions than we could have from one occasion to another. I'm going to take off my statistician hat now and put on my psychologist hat. One of the most important lessons that psychologists have to tell us is this error about personality traits. People think that if person A is friendlier on one occasion, the odds are really very good that they will be on the next occasion as well. And that's wrong. For every trait that's ever been examined, friendliness, honesty, aggressiveness, extroversion, conscientiousness. In a later lesson, I'll talk about why we make this error of assuming that there is great stability for traits. Here I'll just sketch the reason. The main driver of behavior is the situation that we find ourselves in. It's not some internal state that keeps making us behave in like fashion no matter what the circumstances. The party on Saturday night is a different kind of occasion from the committee meeting on Monday morning, and the person who's friendlier on Saturday night at that party is not particularly likely to be friendlier at the committee meeting on Monday morning. Carlos may have been more honest than Edward in one situation, but that's only a very weak basis for assuming he'll be more honest than Edward in some other situation. The mistake here is called the fundamental attribution error. Behavior of a kind that's prompted by the situation someone is in is mistakenly attributed to personality traits. We expect people to be much more of a piece than they really are, and that gets us in trouble. It's interesting to convert these probability judgments to correlations, which we talked about in the last lesson. So I'm going to look at correlations here. That's on the y-axis. And on the bottom, we're going to look at item to item, that is to say, occasion to occasion, and total to total, that is to say, 20 occasions to another 20 occasions. And for abilities, the correlations there, the real correlations, it's about 0.5 for one situation to another, which is substantial. And when you go from 20 situations to another 20 situations, that correlation is 0.95. So if Andre scores more points in the first 20 games of the season, you can bet your bottom dollar he's going to score more points in the second 20 games of the season. People's guesses are right on the money. The correlation is about 0.5 for both basketball playing and for spelling and for other abilities. People's guesses do reflect that they understand the law of large numbers to some degree, but they way underestimate. Correlation has become 0.95. They think it's only 0.75. The situation is very different with personality traits. From one occasion to another, the predictability is only a correlation of about 0.15. It's extremely low. Despite that fact, people really do have personality traits, and if you've got 20 observations across different situations for someone, you can predict pretty darn well about the next 20 observations for that person. But we're hopelessly miscalibrated on this. People think that the correlation is 0.8, very, very high, when it's tiny. And they also have no recognition that the law of large numbers applies here. They don't realize that there's much difference between one occasion to another as opposed to 20 occasions to another 20 occasions. So here's the overall picture. We're accurate at the level of the individual occasion for abilities. We don't quite understand how much more predictability we get when we have more data. But for personality traits, we're wildly miscalibrated for the degree of predictability we get from observation on one occasion to observation on another occasion. In my 20s, I went to London for 10 days. And lucky me, there was blue sky every day. And I came away thinking, the English are really big complainers. They're always talking about the rain. But, I was there for 10 days, and it was gorgeous weather the whole time. But years later, I spent a week in London in November. It rained every day. Oops, I was hasty before. Now, I know perfectly well that the weather is highly variable, every place I've ever spent very much time, but I fail to realize that London is going to be like every other place I know about. That is, the weather is variable. So I failed to realize that I didn't have enough evidence about London weather because I didn't stop and think, wait a minute, what's the variability for this dimension? A few years ago, a cousin of mine from Wisconsin came to visit me in Ann Arbor, and we were talking about where we go for vacations, and I was saying my wife and I really love going to Chicago. And she said, really, Chicago? I saw all those slums from the expressway on the way here. Well, does my cousin not know that cities are variable? Of course she does. She knows every city has some high-rise office buildings, some suburbs, some slums, but she didn't stop to think about that. She didn't stop to think about the fact that the dimension she's trying to make a judgment about is one that's highly variable, and she'd better get a larger sample before she can come up with a conclusion that Chicago is a pretty slummy place. When we get evidence about a person or about a thing, we're likely to use that evidence to create a judgment. So, Madison is really a good bridge player. I had no idea. She's probably good at card games in general, and maybe good at games in general. Maybe she's really very smart. And the sequence here is from an observation to a generalization, something we do dozens of times every day of our lives. Sometimes the generalizations are legitimate and sometimes not. And we can think about every observation of anything as being composed of a true score plus error. Sometimes the error is zero, but nevertheless, that observation is still true score plus the error. This is true for every kind of observation. About Bill's height, get an observation and make a judgment about how tall he is, which is how tall he really is plus whatever error we have. Or the correlation between, or an observation about blood pressure, which, by the way, is extremely variable. If you really want to know what your blood pressure is, you've got to take it over many occasions of as different a kind as possible. Or Danny's spelling ability, or Alice's friendliness. So all kinds of things are variable. Observations of them contain error. Failing to remember this, we overgeneralize from small samples. We do it for lots of things, even for weather and the composition of cities, but we almost always do it for behavior that can be understood as trait-related. I want to talk now about a particularly dangerous type of statistic. In the last presidential race, one of the candidates announced that vaccinations cause autism. And his evidence for this was that he had an employee, and the employee had a child, and the child got a vaccination, and the child was autistic thereafter. That's what I call a man who statistic, as in, I know a man who. The evidence is completely inadequate in this case. You actually require hundreds of cases to come to a conclusion about this because autism, thank God, is a rare occurrence. And you're going to have hundreds of people who are given, by the flip of a coin, they get the vaccination. Others, by the flip of a coin, don't get the vaccination. And the experiment has been done, and vaccination does not cause autism. We're constantly being offered man-who statistics, anecdotal evidence that can't bear the weight that's being put on them. And let's admit it, sometimes we're the ones who do the offering. Smoking doesn't cause lung cancer. Grandma smoked a carton a week and died at 102. That's a man-who statistic. Blatzmobiles are lousy. I have a friend who bought a used one and the transmission went, the next thing the rear end went, the whole exhaust system conked out. Finally sold the thing for junk. Miami isn't safe anymore. My Uncle Max was robbed walking out of a 7-Eleven. And the weather's great in London. I was there for 10 days once. When you hear a man-who statistic, ask yourself, how much evidence is this really? How much evidence would it take to establish the point being made by the anecdote? And that, in turn, is always going to depend on how much variability you think there is for the event in question. So lesson number 2 has been concerned with how you figure out what is the case about some object or person, what's going on. Lesson number 3 is going to be concerned with how you figure out what is related to what. And that's the topic of correlation. Hi, I'm Richard Nisbet, and the course is Critical Thinking for the Information Age. This is lesson number 3 on correlation. We're going to talk about how to estimate correlations and how to draw conclusions about the association between variables. Correlation is one measure of the association between variables. It can vary between -1, meaning a perfect negative relationship. The higher you go on one variable, the lower on the other, and +1, perfect positive relationship. Correlation is only one way to assess association. The simplest way is by setting up a 2-by-2 table. Have a look at this one. So this is the simplest possible way to estimate an association between variables. I collected the data, or actually I made it up, but I coded it, disease A, yes or no, and symptom X, yes or no, and I put them into an orderly table. So what's the association between disease A and symptom X? Put another way, is having symptom X diagnostic of disease A? Does having symptom X make it more likely that you have disease A? So I'm assuming that you've been looking at this, coming to a conclusion. The right answer is that there is no association. Having symptom X tells you nothing about whether a person has disease A. Surprisingly, to psychologists at any rate, whose bread and butter is this kind of 2-by-2 table, as it's called, some people say, yes, there is an association. They look just at one cell of the table. They say, lots of people with a disease have the symptoms. So yes, there is an association. Some people look at 2 cells, and some of those say no, because most people with a disease don't have the symptom. Only 20 of the people with a disease have the symptom, 80 don't. Other people look at 2 cells and come up with the conclusion that yes, there is an association because more people with the symptom have the disease than people without the symptom. Few people realize that a determination of whether there is an association requires all 4 numbers. Specifically, you have to compare 2 ratios, namely the proportion of people with the disease who have the symptom versus the proportion of people without the disease who have the symptom. So going back to look at that table, 20 of the people with disease A have the symptom, 80 don't. 20 divided by 100 is 0.20, so the proportion is 0.20. For those who don't have the disease, 10 have the symptom and 40 don't, so 10 divided by 50 is also 0.20. So there's no association. People with the disease are no more likely to have the symptom than people who don't have it. Don't feel bad if you didn't get that right. The original study here was done with nurses. On the other hand, maybe you will feel bad about the fact that nurses have difficulty with this relatively simple association problem. And that's because very little in their education really prepares them for assessing even this kind of a simple association. So let's try a different problem. I'll show you some data that's been collected, but you code it and tabulate it in your head and see how closely you can estimate several correlations. I'm going to show you some data on people's responses to the Draw a Person test, which psychologists use to find out what kinds of emotional problems people have. The psychologist gives the client a pencil and a piece of paper and asks the client to draw a picture of a person. I'm going to show you pictures drawn by clients, and for each of these, I'll list 2 of the symptoms that psychiatrists reported for them. After you've seen all the slides, I'll ask you what kind of problem you think goes with drawings of various kinds. Your answers should be based on what you've learned about the relationship between the types of drawings people made and the types of problems that they have. You'll see drawings like this. So please examine the following slides carefully. Examine the drawing and take note of the symptoms of the person who made the drawing. There are 36 drawings in all. You'll have 6 seconds to examine each drawing. The series of drawings begins now. Now I'd like you to look at the following drawings and decide which problem is most likely for the person who made each drawing. There will be 2 problems to choose from. Base your decision on what you've just learned about the association between drawings with certain characteristics and problems of a given kind. You'll have 12 seconds for each drawing, beginning now. Let's go back and look at those drawings again. If you said for the first drawing, that person is extremely suspicious of other people, that would be a mistake, because strangely drawn eyes do suggest suspicion, but in this series that you saw, strangely drawn eyes were less likely to be associated with suspicion than normal eyes. If you said, is worried about his masculinity for the second picture, that's a mistake, because exaggerated muscles suggest worries about masculinity, but they were actually less likely to be associated with worries about masculinity than normal muscles. Well, if you made one or more mistakes, you're in good company. Most people make these kinds of errors. That's because we're susceptible to seeing illusory correlations. When we're prepared to see a particular association, we are particularly likely to see it. In this case, funny eyes suggest suspicion, so we're likely to remember the slide that showed this association. Emphasis on muscles suggests worries about masculinity, so that's the slide that we remember. Since we have theories about all kinds of things, we can't trust our memory about associations to tell us what the relationship is. If we have a theory that X goes with Y, we're likely to notice and to remember the cases where that's true, and not notice or not remember the cases where it's not true. So even when the data don't actually support a particular plausible belief, we're quite likely to think it does. The drawings and symptom pairings that you just saw were actually invented by my research team, but the draw-a-person test is real. It was given by psychiatrists and psychologists for decades, even though it is literally worthless. You can't tell anything about anybody from the picture they draw, except that it's a very bad test of intelligence. Smarter people do tend to make better drawings, but nothing else about them predicts anything. So how could they do that for decades, continue to make this error? Well, they never set up a 2x2 table. The slides that showed a plausible association got remembered, and the other ones didn't. And that principle explains why psychologists and psychiatrists believe the Rorschach could tell them something about their client. That's the ink blotch, you'll remember. Some of the alleged associations that were claimed about the Rorschach test were those that lay people would find intuitive. Some were more arcane. They were suggested by psychoanalytic theory. But whatever the origin of a theory, if you expect an association, that's what you're likely to see. Then the erroneous belief about correlation gets sustained because you keep on seeing confirmations. So if it's the draw-a-person test that you've been giving for years, you say, just as I thought, this guy who drew the big muscles is worried about his masculinity. Nailed it. We'll be talking about this kind of problem in Lesson 6. We're subject to what's called a confirmation bias in all kinds of ways. We rest content with confirming data, and we don't think to look for data that might disconfirm our hypothesis. I've seen lots of drawings with big muscles by men who were worried about their masculinity. But how about the drawings with big muscles by men who weren't worried about their masculinity? And how about all the men who were worried about their masculinity who didn't draw big muscles? You have to keep in mind all 4 cells of the 2x2 table. And this fact escaped hundreds, if not thousands, of psychiatrists and psychologists. The plausibility principle is extremely important because we can't trust our casual observations about associations. If an association is plausible, we're likely to see it, whether it's there or not. If it's not plausible, we're likely to fail to see it, even if it exists and is quite strong. This is true even for animals. Dogs are almost impossible to teach that they can get fed if they yawn. That's not been the way dogs have been getting food these many eons. Dogs readily learn to go left at a maze if a light comes on at the left, and to go right when it comes on at the right, but it's almost impossible for them to learn to go left if it comes on at the top and right if it comes on at the bottom. They're prepared to see directions that make sense, left and right. They're not prepared to see left and right matched with top and bottom. Cats readily learn that they can get food by pressing a lever or pulling a string, but it's only with very great difficulty that they learn that they can get food by licking or scratching themselves. Pigeons will actually die before they learn that not pecking at a light will get them food. Pigeons haven't made it this far by assuming that not pecking could ever get them fed. So we've just seen that theories are important. They determine what you're going to be able to see. And if you don't have any theories at all, it's going to be hard to see any kind of association at all. In the next segment, we'll look at the case of when you don't have any theory at all. How easy is it to detect correlations? So what if we don't have any theories about the connection between variables? Are we better at getting the relationship right? Well, in this next demonstration, I'd like you to look at the names of people as they appear on the screen. Try to remember as many names as you can. Were there more names beginning with A or names beginning with Z? Was there an association between position of the first letter of the name in the alphabet and the font size for the name? In other words, were there bigger fonts for names that came early in the alphabet or smaller fonts for names that came early in the alphabet? Think about that for a minute. What do you recall? There was actually a correlation of 0.65 for names and font size. That's a very, very large correlation. The later in the alphabet, the bigger the font. But you don't have a theory about that association, so you're not likely to see it. And that's true even when the events are very clear, as they were here. Couldn't be clearer than there's the name, there's the font. When the timing is right between the events at a given occasion, in this case simultaneously, you see the name simultaneously with the font, and even when the timing is right across occasions, so you don't forget the associations you've seen before. So if you have no expectation at all, you're very unlikely to see a correlation, even though it's staring you in the face. Now, instead of you indicating what the association is, I'm going to tell you about a few associations. They're all real associations. I have no more tricks. Your job is to tell me what accounts for the associations. So in the 1950s, there was found to be an association between the number of popsicles sold in a given week and the number of new cases of polio. Why do you suppose that was the case? I'll let you think about that for a bit. Would it have made sense to ban the sale of popsicles? Couples who spend more time on wedding preparations are less likely to be divorced. Why do you suppose that is? If you have friends who are going to be married, should you encourage them to spend a lot of time on wedding preparations? Pipe smokers live longer than most other people. Why do you suppose that is? Should you take up pipe smoking? There are hugely more fatal accidents per vehicle mile for Ford F-150 pickups than for Volvo station wagons. Why do you suppose that is? Should you advise your friends to stay away from Ford pickups? So let's have a brief quiz. See if you can match the driver with the auto. So does this suggest an idea about why the difference might be there in auto accident rates? Well, for each of the correlations we've just been talking about, there's a big problem. The variables in those examples are confounded with other variables. A variable which is associated with both variables of interest, x and y, and which could explain the association between them. The variable of type of automobile is confounded with the variable of type of owner. It could be the type of owner that so heavily influences the fatality rate of different kinds of autos. And in fact, there are some very strong associations between auto type and owner type. Young males have more accidents than other demographic groups, and they're more likely to be driving sports cars, muscle cars, hot rods, and pickups. Middle-aged women who wear sensible shoes are more likely to be driving Buick sedans, station wagons, and Priuses. But those young guys are dangerous no matter what they drive, and the middle-aged women are relatively safe. So, with the other findings I was just talking about, let's play spot the confound. So we're looking for a C variable which could be causing both A and B. In the 1950s, there was found to be an association between the number of popsicles sold in a given week and the number of new cases of polio. Why do you suppose that was? Can you think of a C variable here? Well, heat would be a pretty good candidate. People eat popsicles in the summer and they go to swimming pools in the summer, and swimming pools is where kids were catching polio in the early 50s. Couples who spend more time on wedding preparations are less likely to be divorced. Why do you suppose that might be? If you have friends who are about to get married, should you encourage them to spend lots of time on wedding preparations? What could the C variable be? Well, in this case, people who spend lots of time on wedding preparations are in general different sorts of people than those who have more hurried arrangements. They tend to be better off financially, they tend to be older when they get married, and they tend to have known each other longer. And all of those C variables are associated with greater longevity of the marriage. Pipe smokers live longer than most other people. Why do you suppose that is? Should you take up a pipe? Well, the C variable here is that very different kinds of people are smoking pipes and other kinds of things, or not smoking at all. People who smoke pipes tend to be people in high status occupations. They lead relatively relaxed lives, and they have better access to health care. So we've started to talk about causality. Disentangling correlation and causality is going to be the topic of the next lesson. How do you prove that some relationship is causal? But first, I want to talk about a statistical concept that applies to both correlations and experiments. If you found a correlation between two variables of 0.35, should you believe that there's a relationship or not? Well, that depends on whether the correlation is statistically significant. Statistical significance is the probability that a result at least as extreme as the one obtained could have occurred given that there is in fact no relationship. That's expressed as p less than some quantity, for example, p less than 0.05, which means the probability that the result obtained, or even a stronger one, could have been obtained even if there's no relationship, is less than 5 in 100. So if I say I've found a correlation of 0.35 between the amount of fish people eat and the number of television shows they watch, is that something you should pay attention to if you're interested in that particular topic of what people eat and what they watch? Now, if the correlation was based on 3 subjects, you wouldn't be impressed. So, I have a friend, Joe, and he eats lots of fish and watches lots of TV, and Bill doesn't eat fish really at all and hardly ever watches TV. You're not going to be impressed. In fact, you would have to have 30 cases in order to reach the 0.05 level of significance. In the next section, we'll be talking about experiments. Research of a kind that's usually essential if you want to do what correlations normally can't, namely, show whether one of your variables actually exerts a causal influence on the other. Hi, I'm Richard Nisbet. The course is Critical Thinking for the Information Age. This is lesson number 4 on experiments. Last week we talked about correlations, how to find relationships among variables. But correlations, as it may have become clear in that lesson, have a great weakness. They normally can't tell us about causality. Usually we have to conduct an experiment in order to be sure about causality. The definition of an experiment is it's a scientific study in which at least one variable is manipulated and at least one variable is measured. For example, to take an experiment that was done decades and decades ago, very important one, give some people iodine and others no iodine and examine the incidence of thyroid problems, which used to be a very serious problem. It turns out if you give people iodine, they don't have thyroid problems so much. And as a result, when you buy salt, it's going to say iodized, and that's to protect your thyroid. Another example from psychology might be pay some children for drawing with magic markers and then examine the extent to which they draw with them a couple of weeks later when they're not paid. What you'll find is that if you pay kids for doing something like playing with magic markers, they're less interested in doing it. You've turned it into work by paying them for doing it. Both of these experiments are examples of the so-called gold standard of research, which is the randomized control design. The experimenter assigns people or things at random to the experimental condition versus the control condition. And if you don't have this requirement met, you don't have an experiment, basically. You're just fiddling around. Because assignment at random means that on average, you've got the same batch of people in your experimental condition or the same batch of things as you do in your control condition. The treatment is the independent variable. The control condition receives a different treatment or no treatment at all. The things that are measured constitute the dependent variables. There can be many different experimental conditions and many different control conditions. It doesn't have to be just one of each. Let's look at some examples of questions that can be examined either with correlational research or experimental research. A lot of health research is of that kind. Multiple correlational studies of a particular health practice and typically a very few experimental studies, because it's a lot easier to do correlational studies. You ask people, do you eat fish? How often? And then you see what their cardiovascular condition is. You can do that kind of study without ever leaving the armchair. And then you compare people who happen to eat one type of food with people who don't eat that type of food. You can compare people who get exercise with people who don't get exercise. You compare people who take a particular supplement with those who take no supplement. Or you can carry out an experiment in which we have randomly selected people eat a certain type of food for a period of time and have others not eat that type of food. The same for supplements. You might think that correlational research and experimental research would normally reach the same results. You can say an awful lot of sentences that are the same about those two types of studies. But in fact, it's surprisingly often the case that it's not true that the correlational result is the same as the experimental result. So let's look at the case of vitamin E and prostate cancer. Vitamin E in the correlational studies turns out to be correlated with a lower likelihood of prostate cancer. So naturally, we're beginning to think maybe vitamin E lowers the likelihood of prostate cancer, but there are all kinds of differences between people who take vitamin E and those who don't. Sounds like a healthy thing to do, take that vitamin. And people with more money are more likely to be taking the vitamin E. And more money is associated with lower mortality for almost everything. People who are more educated, paying attention to what the health journals are recommending, are more likely to do that. More educated people tend to take better care of themselves, have better diets, and so on. So it's really very problematic to just say people who take vitamin E are less likely to have prostate cancer, because there's so much else that could be different, so much in the way of a confound, like we talked about in the last lesson. What you have to do is to apply the gold standard of research, which is the randomized control experiment. You flip a coin, proverbially, sometimes these days you would use a random generator device, to see who gets the experimental treatment and who gets the control treatment, and then you measure the outcome. Now, the beauty of the experiment is that we know that people in the experimental condition are essentially the same people as the people who are in the control condition, because they had an equal chance of being in one condition versus the other. So we're going to have equal social class on average, equal number of rich people between experimental and control conditions, identical diets on the average, because they're just people who have a particularly good diet, they're going to be equally likely to be in either condition. So when you do this experiment, you get rid of all the possible confounds, and what you find is that vitamin E makes prostate cancer more likely. This kind of pattern happens quite often. For example, with hormone replacement therapy for menopausal women, a couple, 3 decades ago, doctors started giving women hormone replacements as their hormone status changed. And it was found that women who had the hormone replacement therapy had less cardiovascular disease. So hundreds of thousands of women, partly on the basis of that finding, were given hormone replacement therapy. When you do the experiments, it turns out hormone replacement therapy increases cardiovascular illness. The same kind of story is told for supplements of all kinds. Selenium for prevention of cancer. Yeah, the people who take selenium just because they thought it was a good idea are less likely to have cancers of various kinds. But the experiments show it's useless. The same thing is true for glucosamine for arthritis, vitamin C for prevention of the common cold, vitamin B12 for cognitive function in the elderly, and so on. In fact, most of the supplements that have ever been tested, you find effects in the correlational studies, but not in the experiments. And when you do find effects in the experiments, They're usually much larger in the correlational studies. This generalization, by the way, all of these generalizations that I've just been making, apply to healthy people with an adequate diet. If you've got a selenium deficiency, you're going to be better off if you get some selenium. But if you're just an ordinary healthy person with an ordinary healthy diet, very few supplements are going to do you any good. There are actually 50,000 supplements on the market. Hardly any of them are tested. Our government does not require testing of supplements. It doesn't even require you to put selenium or whatever in your pill. You can put sawdust. And indeed, there are some major chain stores where you're going to get sawdust rather than selenium. And here's a fairly exhaustive list of the ones that have actually been found effective. Probiotics for gut health, zinc for shortening duration of colds, CoQ10 for cardiovascular health, fish oil for cardiovascular health and various other purposes, zinc for a number of purposes, vitamin D3 for prevention of fractures in the elderly. If your supplement is not on this list, I suggest you go to Cochrane Reviews or some other medical website which can tell you what would be a good supplement to be taking. This applies not just to supplements, but to every kind of health practice. You may have heard that it's very important to have breakfast because you're healthier that way and less likely to be obese. And the theory about that is that if you don't have breakfast, you're starving later in the day, so you overeat, you overshoot what you should have. And in fact, all the correlational studies show that. But the experimental studies show there's no difference. So if you want to skip breakfast, go ahead. It will not make you fatter. By the way, where do you suppose the idea came from that it's very healthy to eat breakfast and very important for keeping weight down? The idea of John Harvey Kellogg, who wrote this hypothesis, or actually he wrote it as a finding, in his health journal. Mr. Kellogg was the inventor of cornflakes, so there may have been a connection with why he felt it important to tell people that breakfast is a big deal. So what's going on? Why are the correlational studies finding one thing and the experimentals another? Well, vitamin E is confounded with social class, with education, with better health practices, and with all that goes with those things. The problem here is called self-selection. People choose their level on the independent variable, and they bring along with that their level on a host of other variables. So I take vitamin E, but that's, I'm paying attention. That sounds healthy. I can afford vitamins. I'm the sort of person who's very concerned about health. I eat a very healthy diet. I do exercise and so on. In fact, this bias is given the name healthy user bias. Anything that people think is healthy is going to be associated with health because the people who care about health and can afford to be healthy are doing it. If Science magazine were to announce next month that people who eat brandied pretzels for breakfast live longer, in 10 years it would be true. The people who ate brandied pretzels for breakfast would live longer because they read Science magazine or the New York Times, which reports that to them. You can even speak of self-selection for things. It sounds a little bit weird, but you can talk about that Ford pickup as self-selecting its driver, the Volvo wagon as self-selecting its driver, and they're self-selecting different kinds of drivers. The people who did those correlational studies, by the way, probably didn't think that the experiments were necessary because they didn't look just at one correlation. It's not quite as simple as the way I described them. They just didn't just look at people who took vitamin E and who and then looked to see whether they had prostate cancer. They did what's called controlling for possible confounding variables by using multiple regression analysis. Multiple regression analysis examines the association of each of a number of variables with the target independent variable x, with a target-dependent variable, y. The additional variables are controls. Multiple regression analysis looks at the correlation of x and y, controlling for all variables that are correlated with both x and y. It does this by subtracting out of the correlation between x and y the correlation between each of the other independent variables with both the x and the y variable. There are huge problems with multiple regression analysis. Typically, you can't identify all the possible variables that might be correlated with the target independent variable and the target dependent variable. You often can't measure some variables you really assume are important, and often you measure them with such poor reliability or validity that the results are distorted. If you measure a variable with zero validity, so that it has no real meaning at all, if you control for it, you'll find it doesn't make any difference. So you control for that variable. Well, you didn't control for it if it has no validity. And many controls have very low validity in practice. And it's meaningless to say you control for variables with missing variables, which is often the case. How many old ladies are driving pickups? How many tough young guys are driving powder blue Volvo station wagons? I want to stress two things about multiple regression analysis. Most science and health writers don't understand the extreme weakness of multiple regression analysis. They don't know when to alert you as to whether the method used in the study was dubious, namely based on multiple regression analysis, or solid, based on the gold standard experiment. And as a matter of fact, many scientists don't understand the weakness of multiple regression analysis. They do it feeling like they have done their controls and they feel confident that the result is meaningful, when it often isn't. You're constantly being told by the media about research which is meaningless or worse. Ask yourself about a reported finding. Is this correlational or experimental? If the report doesn't say which it is, probably it's correlational. And if the finding is correlational, it's quite likely to be wrong, at least when the finding concerns biological research or research on human behavior. In 2008, when Obama first began campaigning for the presidency, early on he went to Google and spoke to all of their employees, had a question and answer session with them. Eric Schmidt, who was the CEO, as a joke for the first question, asked him, what's the best way to sort a million 32-bit integers? Obama said, well, I think bubble sort would be the wrong way to go. Schmidt hit his forehead. The audience applauded. Obama went on to say, I'm a big believer in reason and facts and evidence and science and feedback. In the audience that day was a man named Dan Soroker, who decided on the spot to go to work for Obama. As he said, he had me at bubble sort. He had something from Google to offer Obama. It's called A/B testing. When you don't know which of two courses of action is best, you flip a coin and you present one group with one and one group with the other. Google is doing hundreds of experiments at any one time. What gets the best results for them? And you do what the experiment says is superior. They have a derisory expression at Google for how most companies make most of their decisions. They get the hippo. That's the highest paid person's opinion. Here's how A/B testing was carried out in the Obama campaign. Which combination of image and text do you think got the most clicks on the Obama website? Well, one of the possible images was a turquoise portrait of Obama. Another was a black and white photo of his family. And another was a brief video of him giving a speech. And the text could be either learn more, join us now, or sign up now. Do you have intuitions about which of those are best? I actually find I don't, but it doesn't matter because I would probably be wrong. What's the most effective is the black and white photo and learn more. As a matter of fact, it's 40% more effective. That's huge from the standpoint of campaign financing. But businesses of all kinds can do A/B testing as well. In grocery stores in the US, almost all have aisle 4 for sodas, aisle 6 for soups. Like kinds of foods are in like aisles. How else could you do it? Well, the Japanese do it quite differently. They arrange things by type of meal. So Japanese miso soup ingredients are all sitting in one place. Italian food ingredients are all sitting in another place. So which is better, aisles or this more holistic way of arranging food displays? Well, you might think, well, probably the aisles are better for Americans and maybe the holistic way is better for Japanese. That's actually not the case. The holistic way is much more effective for Americans as well, because they were going to make Italian food. They got home and said, "Oh my God, I forgot the Romano cheese." The supermarket takes care of that. So and also, by the way, this is not only good for the supermarket. They sell that Romano cheese, but it's good for you because you don't then have to say, missing the Romano cheese, I'm going to have to have a TV dinner or eat a bowl of cereal. One very enterprising grocery store in El Paso, Texas, decided to try to find out if they could sell more fruits and vegetables than they do. That's doing a good deed if they get people to do that, because fruits and vegetables are better than most of the rest of the things they could be eating from the supermarket. But it would also be doing well by the supermarket owner because the profit margin, is higher on produce than it is on other things. Well, one of the things he tried was signs saying that the average shopper buys X number of dollars of produce. That increases sales. Or he tried putting a divider in the cart saying, place fruits and vegetables in front of cart. That actually doubles sales. Whatever business you're in, there are going to be opportunities to experiment instead of just getting the hippo. You also need to be conducting A/B testing on yourself. When I was in college, I had a roommate who, when he had an exam the next day, he felt it was terribly important to get a good night's sleep. But he would be sort of worked up, so he'd lie in bed, and he's having trouble getting to sleep. So he would get out of bed and do 40 push-ups to make himself tired and get back into bed and lie there for another 20 or 30 minutes without sleep. As I guessed at the time, it's a perfectly terrible idea to try and exercise and then try to go to sleep immediately after, because your physiological arousal level after exercise lasts for 20 or 30 minutes, and it's going to keep you awake. Should you work right up until bedtime, or should you always quit well before bedtime to get relaxed? I know what it is for me because I flipped the coin. If I work until I'm exhausted, I lie in bed and continue working as opposed to sleeping. Should you get out of bed when you're sleepless, or should you stay in bed? It's so tempting to stay in bed. I mean, I don't want to get up out of bed. I need all the sleep I can get tonight. Flip a coin and try getting out of bed. If it comes up heads, staying if it comes up tails. You may find what I have, which is that you're much better off to get out of bed and read a book. Typically within an hour, I'm tired, I go back to sleep. Whereas I can lie and toss and turn, annoyed at myself for not being able to sleep if I'm going to stay in bed. Should you go to sleep in a warm room or a cold room? by the way, that's a very big, what we call main effect there. That is, most people sleep much better in a cold room than a warm room. Does coffee make you more efficient, or does it just make you more jittery? You're probably not going to find out without A/B testing. People's response to caffeine, by the way, is very different. It's actually a soporific for some people, makes people more relaxed, puts them to sleep. That's not common, but there are wide varieties of ways of responding to caffeine. Does yoga have good effects on you? We'll try the A/B testing. Do yoga for a week and no yoga for another week, or do it for 6 weeks and no yoga for 6 weeks. Is meditation good for you? Does it make you a better person? Does it make you more relaxed? Does it make you more efficient? Flip a coin before you decide whether to meditate today or this week or not. Are your papers better when you start with an outline, or is it better to just jump into it? This can go on forever, of course. All kinds of things that are important to us that make us more efficient, that make us happier, are subjects for experiments. They're possible topics for experiments, and they're eminently worth doing. So if you want to know what's going on, you can't just observe the world. You can't even just be systematic and look at correlations. Usually, you have to do an experiment in order to be sure about what is causing what. In the next segment, we'll be talking briefly about some technical points about experiments, and we'll be talking about two topics which are dear to my heart. One is the fact that natural experiments are occurring around us all the time, and we can make use of those. And the other is how important it is for society to do more experiments than it does. We pay huge prices for the experiments that we don't do. Well, before we leave the topic of experiments, I want to talk about two concepts. One is the concept of within versus between designs of experiments. The conditions of an experiment have either a within design or a between design. In a within design, all people or all things that are studied participate in all the conditions. In the between design, people or things that are studied participate in only one condition. There's a huge difference between these conditions in terms of their power, that is, the likelihood of showing a difference if there really is a difference, because the error variance is greatly reduced. If you're looking at Joe in the experimental condition and Joe in the control condition, he's the same person. The only difference is the experimental versus control condition. But if you're looking at Joe in the experimental condition and Bill in the control condition, all kinds of things differ between them, and it makes your results noisy. The treatments differ, but so do the people. Unfortunately, it's usually impossible to have a within design. Fortunately, the experiments that you do on yourself have a within design, so they're really quite powerful. Second concept I want to talk about is statistical independence. If you do an experiment in which there are 40 students in one classroom who are taught in the usual way, and 60 students in another class who are taught using a new method, what is N? The number of cases. Unfortunately, it's not 100. It's 2, because N is the number of cases for which the results are not influenced by other cases. For example, in that algebra study, if one student in one of the classes spreads mononucleosis, then everybody's affected by that. Many people are affected by that. So what happens to that student is going to happen to lots of others. Or if the student is extremely disruptive in one of the classes, this would affect many or all of the other students. If the same study were done with MOOC instruction, the results would be independent and the number of cases would be 100. So Jane in Shanghai takes the course and Joan in London takes it, they're not influencing each other. The results are independent. So the N is the number of people who are in the study. There's no way to establish statistical significance if case results are not independent of one another. In fact, you don't have a study, really, or you have only a study which is a glorified anecdote if the case results are not independent of each other. Let me just note that there's a great general importance of this statistical independence point. You need to know whether a given type of event is characterized by independence or dependence. My grandfather was a farmer in Oklahoma, and he grew wheat. And one year he was hailed out, as they say. Hail destroyed his whole crop. But he didn't buy hail insurance at that point, which many people had, because it just was so unlikely that hail would happen twice in the same place. But in fact, it did, and he was hailed out the next year. But then he's thinking, well, it couldn't possibly happen 3 times. Lightning doesn't strike twice in the same place. Hail doesn't wipe somebody out in a particular location 3 times in a row. But unfortunately, it did. And as a result, I'm a psychologist rather than a wheat baron. So the idea that my grandfather had is called the gambler's fallacy. The gambler at the roulette table who sees red and red and red and red feels confident that the next one surely is going to be black. I mean, that's just so atypical, red, unless the house is trying to cheat. But in fact, they're completely independent events. Those 4 reds just happen to come up by chance. Every trial, every turn of that roulette wheel gives an independent trial, red or black. Parents often feel that, I've had 2 boys, I'm due a girl. Well, unfortunately, that's gambler's fallacy applied to births. Births are independent events, and so there are no more. After you can have 8 or 10. Actually, I know a family, believe it or not, in Detroit, which had 11 girls. They kept trying. It's great having these girls, but surely the next one will come up a boy, and it never did. The final concept I want to talk about is the concept of natural experiments. A couple of years ago, the channel CNN had a program where they argued that you should minimize the contact of babies with bacteria and viruses. Very bad for them. You don't want your baby to get sick. And then I happened to be watching Canadian TV news about a month after that, and they were arguing that babies who come into contact with a wide range of bacteria very early in life appear to be at a lower risk of developing allergies later. Well, it would be great to do the experiment. Say Mrs. Jones would like to flip a coin and determine whether your baby will be exposed to a lot of bugs or not. Would you like to let us do that? She'll probably say no. It's a hard experiment to get done. But suppose you knew that Russians are less likely to have allergies than Finns. Suppose you knew that farmers are less likely to have allergies than city folks. Suppose you knew that children who went to daycare were less likely to have allergies than those who didn't. And suppose you knew that children who had had lots of diarrhea as a baby were less likely to be allergic than those who didn't. Or suppose you knew that babies born vaginally were less likely to be allergic than babies born by cesarean section. Now, do you see what these are building toward? All of these things, they're different in very different ways, Russians are different from Finns in God knows how many ways, but as it happens, one of them is they're just less hygienic. The Finns, everything's spick and span in Finland if you go there, and that's not really true in for Russians. Farmers, what characterize are different in all kinds of ways from city folks, but they don't have such a cleanly environment. There's really animal poop everywhere. Children who went to daycare differ sometimes, in some ways, undoubtedly, from those that didn't. But children who went to daycare were getting a very buggy environment. Here, how would you like to play with my mucus-covered truck? Children who had lots of diarrhea probably had that diarrhea because they had lots of bugs, and those that didn't have so much diarrhea probably had less. Babies born vaginally are exposed to a much wider range of bacteria than those who are born by antiseptic cesarean section. So these are all natural experiments on the effects of exposure to bugs. Bacteria and viruses, by the way, early in life, seem to lower the risk not just for allergy, but for other autoimmune disease, such as asthma. So are you ready to get your baby dirty after hearing about all these natural experiments? A real experiment is in order, but it's going to be hard to do that one with babies. So you use what's called an animal model. And one study has been done which provided mice with germ-free environments. That's as compared to control mice. And I can assure you that mice do not live in laboratories with germ-free environments. You have to take a lot of steps to get that. And the results are that you might be surprised to know that mice can be allergic and they can have asthma, and they are much more likely to if they were raised in the germ-free environment. An extremely important illness is called irritable bowel syndrome. That's another autoimmune disease of the gut. As it turns out, the richer the country, the more the irritable bowel syndrome, which is no joke because it can be fatal. So if lack of bacteria in the gut is the problem, how to solve that? And someone did the actual experiment here. They provided the contents of someone else's gut into an IBD sufferer's gut. And fortunately for the experimenter, as well as for the patient, it worked. And that's one of the main findings that have led to probiotics being commonly taken for gut problems. You take lots and lots of bacteria, and that's good for your gut. Another one of my favorite natural experiments was done in the Chicago projects for lower income people. Someone found that people who lived in projects that were surrounded by asphalt and concrete were subject to much more violence and robbery in their project than people who lived in projects that were surrounded by greenery. Now, is that an experiment? Not quite. Although, as it happens, the Chicago Project Authority people say they really do assign people at random. If that's the case, then it's not just a natural experiment, it's a real experiment. And of course, there's the granddaddy of all natural experiments. In the 18th century, the physician Edward Jenner in Britain happened to notice that milkmaids didn't get smallpox. Now, why might that be? Well, the most distinctive thing about milkmaids is that they're hanging out with cows all the time, and they get cowpox, which is a related disease to smallpox. So Jenner bravely infected a 10-year-old boy with cowpox and let him get the illness, and then a few months later infected him with smallpox, and he didn't get smallpox. And that's why you and everybody else virtually in the world have been given Jenner's smallpox vaccinations. By the way, vaca means cow. So your vaccination is related to the cows that those milkmaids were getting their immunity from. And I now want to end on a note that is very important to me, which is that we pay very dearly for the experiments that don't get done or don't get done right. The U.S. to this point has paid $200 billion for children to be in Head Start. And we don't actually know whether Head Start does kids any good or not, because no one ever did the experiments. We do know that some forms of child care or early childhood education are very effective. They produce a gain when you do the actual experiment. They produce a gain in academic success, which is really very great, among the best programs, increasing enormously the likelihood that kids will graduate from high school, enormously increase the likelihood that they'll graduate from college. We just don't know whether those Head Start programs are like those programs. So we don't know, and we could have. With a few $1 million, we could know the answer, or we could know exactly what kind of Head Start program would be most effective. On 9/11, or in response to the events on 9/11, 9,000 grief counselors descended on New York to offer them a program that seems to me to be a very good idea. They met with small groups of people who had suffered these terrible events. They had people talk about their experiences and share the emotions that they had. The grief counselors assured them that these kinds of emotions were normal and that in the not too distant future, they would be much less unhappy, much less distraught by these events that had occurred. It turns out, however, that when you do the actual experiments, literally flip a coin, Jane gets grief counseling, Joan doesn't, that grief counseling actually prolongs grief, prolongs unhappiness. Now, as a psychologist, I could certainly come up with a lot of reasons why that might be the case, but it doesn't really matter why it's the case. The implication is perfectly clear. Grief counseling is something that should not be done, at any rate, the way it's done now in the United States. About 20 years ago, prisoners in New Jersey had what seemed to me like a terrific idea. They got junior high school kids to come to the prison and told them how horrible prison is, how boring it is, how bad the food is, and how much violence they have to deal with, and so on. Sounds like a great idea. Actually, however, from that very first study that was done, it turned out that kids who had been through what's called the Scared Straight program were 13% more likely to be involved in crime than kids who didn't go through the program. There have now been a dozen studies, and the estimate is that for every dollar paid on Scared Straight, society pays $400 in prison costs and in loss of property. Well, the next lesson is going to make use of pretty much everything we've been talking about to this point, namely how to make accurate predictions. Hi, welcome to Lesson 5 of Critical Thinking for the Information Age. We'll be talking about prediction today, how to predict what will happen in the world more efficiently than we sometimes do. We'll start the lesson with a quiz. Then we'll go back through the items on the quiz and see how you did and whether it would be possible to improve on your performance. There is a phenomenon called the Rookie of the Year, jinx. In American baseball, the Rookie of the Year, he's the best player for the year, is only rarely the best player the next year. The phenomenon is called the sophomore slump. Why do you suppose it occurs? Please say your answer out loud, or better still, write it down. Second problem is about my friend Catherine, who's a foodie. She enjoys eating in fancy restaurants, but she finds that when she has a really excellent meal in a restaurant, subsequent meals are rarely as good. Why do you suppose that is? Please say your answer out loud, or better still, write it down. One more quiz item. It's based on a true story. A psychologist was once lecturing a group of flight instructors. He told them that psychologists have found that skill training goes better when you give rewards for improved performance. That's more effective than giving punishment for mistakes. One of the instructors immediately raised his hand and said, "Lots of times I've praised flight cadets for clean execution of some aerobatic maneuver, and the next time they try the same maneuver, they usually do worse. On the other hand, I've often screamed into a cadet's earphone for bad execution, and in general he does better on his next try. So please don't tell us that reward works and punishment doesn't, because the opposite is the case." So are you inclined to believe the psychologist or the flight instructor? Let's go back to the sophomore slump. The baseball Rookie of the Year is only rarely the best player next year. University of Michigan students who've had no statistics always give causal interpretations of this. They say, well, maybe the pitchers make the necessary adjustments, or maybe the guy gets too cocky. But let's go back to our old friend, the normal distribution. How did the Rookie of the Year become the Rookie of the Year? Well, first of all, by having more talent, for sure, than the average person, a lot more, but everything went his way that year. He's way off here at the one end of the continuum, but in that space in there, the really very top space, there's lots that can go right or can go wrong and that can affect your ultimate performance. Everything went his way that first year, the Rookie of the Year. He got ideal coaching. He happened to do extremely well his first few games. That built his confidence. He got engaged to the girl of his dreams. But the next year, he got an elbow injury, and I'm sorry to say his fiancée broke up with him. So somebody else got all the breaks. Somebody else was way out there on the end of the continuum. Being Rookie of the Year is an observation. It's an observation based on a very large number of behaviors, but it's still an observation. And like all observations, it needs to be thought of as being composed of true score plus error. Or, to put it in a way that makes more sense in this case, the observation, best that year, is true score plus luck. So the Rookie of the Year had a lot of things that boosted his performance that were constituted error with respect to what his true score is, or good luck. The next year, the luck didn't contain such an imbalance. His luck dealt him a new hand. Some other super talented player got all the breaks. The error was on their side. The concept here is the concept of statistical regression. Extreme events of a type that is distributed normally will be followed and preceded by less extreme events, to the extent that the events are subject to chance influences. To help think about the Rookie of the Year problem, suppose we looked at the best players the second year. Would they likely have been the best player the first year? No, because regression works in both directions. And it would be silly to look at the best player the second year and find out that he wasn't quite so good the first year and declare that there must be a freshman slump. No, there's no slumps here. There's no jinxes. There's just, so far as we know, when we certainly know there's regression going on. So let's return to my friend Catherine, who's often disappointed when she has a second meal at a restaurant where the first meal was excellent. Most University of Michigan students with no statistics will say, again, they're trying to make a causal interpretation. They'll say, well, maybe the chefs change a lot, or maybe her expectations just got too high and the meal couldn't meet those. Well, meal quality is a variable, and excellent is an extreme value on that variable, and you have to expect that the next meal will be less extreme. To help you see that, think about whether you believe there are more restaurants in the world where you always get excellent meals, or more restaurants where you sometimes get excellent meals. If it's sometimes, then if her first meal at the restaurant was excellent, odds are that's one of the restaurants where you only get excellent meals sometimes, and your expectation for the next meal is that it's going to be at least slightly less good than the first. And about that pilot training, an extremely good maneuver is going to be followed on average by something less good, and an extremely poor maneuver is going to be followed by something less bad. That's what regression is all about. So it's the psychologist who's right. The flight instructor failed to recognize that the phenomenon of regression creates an illusion of causality. Anything that happens before you get a less extreme event after an extreme one is a candidate for phantom causality. Incidentally, the regression principle tells us that we give too much credit to doctors. Most diseases are self-limiting. They go away by themselves. But we're likely to credit the cure to the doctor's treatment. And the doctor can be pretty sure that even if the treatment is a sugar pill placebo, the patient is going to get better, and thank the doctor. Regression also helps to keep all kinds of nostrums and homeopathic remedies popular. I had the flu and I took snake oil and cleared it right up. I went through a period when I kept getting headaches, and I started putting Wolfsbane on my cereal, and they went away. Notice there's a bit of a man-who statistic quality to some of these things as well. Now let's talk about a slightly different kind of problem. Namely, cases where there is more than one variable that you're trying to think about, or more than one object or person. Again, we'll start with a quiz. Highly intelligent women tend to marry men who are less intelligent than they are. Is that surprising to you? Why do you suppose it's the case? Please say your answer out loud, or better still, write it down. Suppose I told you that the correlation between the intelligence scores of spouses is less than perfect, less than 1.0. Would that be surprising to you? There are a number of tests of sense of humor that have been created by psychologists. Your lecturer, that's me, has a student who took one of these tests and scored at the 98th percentile, indicating that he had an extremely good sense of humor. What do you suppose is his percentile score on a test of IQ that he took at about the same time? Again, please say your answer out loud, or better still, write it down. What do you suppose is the correlation between sense of humor and IQ? Does your answer make you inclined to change your prediction about the student's IQ score? Based on the regression principle, you now understand that extreme scores on a particular variable don't directly predict future scores on that variable. This also goes for predicting one variable from another. Usually, the correlation between variable A and variable B isn't 1.0, but we treat it that way sometimes. People are sometimes surprised that extremely tall people have children who are considerably shorter. but they shouldn't be. The regression principle holds when we're talking about two variables, just as it does when we're talking about one variable. And the regression principle holds when we're talking about more than one object or person, like father and son, for example. If a man is 6'4", what's the best guess as to how tall his son will be? You know almost enough to figure that out. Let me remind you that the mean for male heights in the U.S. is 5'10". The standard deviation is 3. So 6'4" is 2 standard deviations from the mean. And recall that the correlation between heights of fathers and sons is 0.50. Well, actually, of course, what I told you about is the correlation between the heights of mothers and daughters, but it's the same for fathers and sons. So you only need to know one more thing to know what is your best prediction for the height of that son of the very tall father. We know we have to go halfway from the mean, that's 0.5 of the mean, to get the prediction for the son's height. That's 1 standard deviation, and the height at 1 standard deviation is 3 inches above the mean, which is 6'1". So here's how to estimate one value from another which is more extreme. Find or estimate the correlation between the two types of events. Go that far away from the mean in the direction of the extreme value to get an estimate of the value you're trying to predict. So if the correlation is 0.5, you go halfway from the mean to the more extreme score. If the correlation is 0.3, you go 0.3 of the way from the mean to the more extreme score. So let's go back to the fact that highly intelligent women tend to be married to men who are less intelligent than they are. Most people find that surprising, and once they know it, they immediately start trying to looking for causal interpretations. Say, well, maybe some women who are really super bright, maybe they don't really want to have the light shining on somebody else all that much. I mean, I've heard a dozen different causal interpretations. But did you find it surprising that the correlation between spouses' IQ was less than perfect? Probably not. It's too easy to think of exceptions to that. And in fact, the exceptions are the rule, because the correlation between spouses' IQs is only a little more than 0.3. Let's say 0.33 for ease of calculation. So if you know that a particular woman has an IQ of 130, which is 2 standard deviations from the mean, that's 100 plus 15 plus 15, what is the expected value of her husband's IQ? Well, back to the normal distribution, the metric we use to measure IQ is defined in standard deviation terms. So we go 1/3 of the way from the mean to 2 standard deviations above the mean, that's 130. So we go to 110. That's 100 plus 1/3 of the difference between 100 and 130. Notice that imperfect correlation means regression is a certainty. If the correlation between two variables is less than 1.0, which it is for almost everything that we can apply statistics to, then extreme scores for one variable will be less extreme on the correlated variable. But bear in mind, the regression principle can only tell you your best expectation. After all, some truly brilliant women are married to men who are even smarter. But most truly brilliant women are married to men who are merely bright, and most truly brilliant men are married to women who are merely bright. So let's go back to that test of sense of humor. This student scored the 98th percentile on it, and I asked you what his percentile score would be on an IQ test. An awful lot of people say the 98th percentile. But of course, that could only be true if the correlation between sense of humor and IQ were 1.0, literally perfect. The person with the highest score on sense of humor has the highest score on IQ, the next highest score on sense of humor, the next highest IQ. Nobody believes that. So expected IQ couldn't possibly be 98th percentile. It has to be less than that. And to come up with a good guess as to what it should be, estimate what you think the correlation is. What would you think it would be? I think it's probably no more than about 0.5. So I should go 0.5 of the way from the mean, which is 50th percentile, to the 98th percentile, which is one standard deviation away from the mean, which is the 84th percentile. That's my best prediction. So to summarize this, extreme values will likely be followed by or associated with less extreme values on average. The more extreme the value, the more likely it is that other values on the same or different dimension will be less extreme. The lower the correlation between dimensions, the greater the regression from one dimension to the other. Note that if the correlation between two variables is 0, you have to predict from even the most extreme value on one variable that the value on the other variable is at the mean. So if the correlation between number of movies that people go to and their height is 0, even if a man goes to 500 movies a year, his expected height is 5'10". In the next segment, we're going to talk about another non-obvious statistical concept that's necessary for all kinds of prediction purposes, namely base rate. So let's talk about base rate. It's a concept that's critical to many prediction problems. Again, we'll start this segment with a quiz. Imagine that a physician has administered a test for prostate cancer to a very large number of men in their 50s. He finds that if a man has cancer, there's an 80% chance that the test will reveal it. That is to say, an 80% chance that the man will test positive for cancer. So Charles, who's 53 years old, has taken the test and it comes out positive. So what's the probability that Charles has prostate cancer? The answer is we can't possibly know, because we also have to know the probability that a man will test positive for cancer when he doesn't have it. And in fact, almost all medical tests do produce such false positives, they're called. So let's say you know that the false positive rate is 10%. 10% of men who test positive do not in fact have prostate cancer. So the question is, what is the probability that Charles has prostate cancer given that he tested positive? We still can't know, because we also have to know the base rate for prostate cancer in the population in question. Let's say the base rate is 1%. 1% of all men in their 50s have prostate cancer. That's the base rate. So now, what is the probability that Charles has prostate cancer given that he's tested positive for it? We can actually now answer the question, although it's complicated. To make it simpler, let's think about a population of 1,000 men. And the statistics I'm about to show you are not real ones. They're just chosen to make it reasonably easy to figure out the probability that someone has the disease given that a test says the person does. So it's another old friend here, a 2x2 table. We have some people who get a positive test, yes, some people who do not test positive, and we have some people who have cancer and some people who don't. And we're trying to predict the likelihood that someone has cancer when the test says he does. So we've got 1,000 people. We know that 10 of these people, that's 1 in 100, have cancer, and 8 of them have been correctly diagnosed with it. That's 80% of 10, which is 8. 2 of them have been incorrectly diagnosed. They have cancer, but it doesn't show up. Then we know that a total of 990 men don't have cancer. We know that 10% of those men are going to get false positives. So 10% of 990 is 99. Now, how do we find out whether Charlie actually has prostate cancer? Well, we divide the number of men who have prostate cancer and test positive by the total number of men who test positive. That's 8 plus 99. And the rate there is 0.008 divided by 0.008 plus 0.099, or in numbers, 8 divided by 107, which is 7.5%. So Charles, who was panicked when he heard a test that correctly identifies men who have prostate cancer with 80% accuracy, and he has been identified with having prostate cancer, he's going to be relieved when he finds out that the actual probability that he has cancer is not 80%, it's only 7.5%. So if you're given a positive diagnosis for some disease, here's what you need to know. You must know the percent of people who have the disease who will correctly test positive, the percent of people who do not have the disease who will incorrectly test positive, and the overall percent of people who have the disease. That's the base rate. Then you divide the number of positives who have the disease by the total number of positives. If you were unable to figure out the probability that Charles has the disease, given those three numbers, the good news is that most physicians can't figure that out either. But of course, that's also bad news, because many of those men who are false positives are going to have biopsies, which involve some risk and some discomfort. So testing has its dangers. A decision about whether to test depends on knowing what fraction of men who test positive and do in fact have the disease would have died of it. And in fact, a very high fraction of men who test positive with currently available techniques would not have died of the disease. As a consequence, the government is now recommending against routine testing for prostate cancer. The exact same logic prompted the government recently to recommend that there should not be routine testing for breast cancer for women below the age of 40. And I should say both of these recommendations were met with anger and disbelief on the part of many people. It's safe to say, however, that most such people were not sufficiently aware of the implications when the disease has a low base rate of occurrence, it's uncommon, the disease has a high false positive rate, further diagnostic procedures pose problems, and even if you have the disease, you might not die from it. Now let's look at another kind of problem. A cab was involved in a hit-and-run accident at night. Two cab companies, the green and the blue, operate in the city. You're given the following data. 85% of the cabs in the city are green and 15% are blue. A witness identified the cab as blue. The court tested the reliability of the witness under the circumstances that existed on the night of the accident and concluded that the witness correctly identified each one of the two colors 80% of the time and failed 20% of the time. What is the probability that the cab involved in the accident was blue rather than green? Please say your answer out loud or write it down. And now a similar problem, panel truck problem. A panel truck was involved in a hit-and-run accident at dawn in an alley behind a restaurant. The only panel trucks that come down that alley are the white ones of the Pacific Bread Company and the yellow ones of the Mountain Milk Company. You're given the following data. The white Pacific trucks cause slightly more than 5 times as many panel truck accidents in the city as the yellow Mountain trucks. A witness identified the truck as yellow. The court tested the reliability of the witness under the circumstances that existed in the early morning hours of the accident and concluded that the witness correctly identified each one of the two colors 80% of the time and failed 20% of the time. What is the probability that the truck involved in the accident was a yellow Mountain truck rather than a white Pacific truck? Okay. So I hope you didn't say that for the cab problem, that there's an 80% chance the cab is blue, because the base rate for cabs blue cabs versus green cabs is only 15%. So you have to take that into account somehow in the problem. To see that, suppose the percent of cabs that are blue was 1/2 of 1%. Very rare, in other words. So 99.5% of the cabs are green. And the witness is wrong 20% of the time. This means that a very high fraction of the time that the witness says the cab is blue, it's actually green. In fact, nearly every time that the witness says it's blue, it's green. So you have to take into account the prior odds for blue, or the base rate for blue. The actual probability that the cab is blue, given that the witness says the cab is blue, is a little tricky to calculate. But it's actually the same procedure that we used for the prostate cancer diagnosis. Let's assume that there are a total of 100 cabs in the city. We're going to set up a 2x2 table. So the witness says the cab is blue, or he says it's green, and the cab is in fact blue or in fact green. And we know that 15 of these cabs are blue and 85 are green. We know that 12 of the cabs that the witness says are blue because he's right 80% of the time. 80% of 15 is 12. And we know in 68% of these incidents, when the witness says the cab is green, it is green. That's 80% of 85. And we know that 17 times when the witness says it's blue, it's actually green. And 3 times when the witness says it's green, it's actually blue. So how do we figure out the likelihood that that cab is blue, given that the witness said it's blue? We know that we need to divide the number of times that the witness says it's blue and the cab is blue by the number of times that the witness says it's blue, and the number of times the witness says it's blue, but it's green. That's 12 divided by 29, which is 0.41. So, given that a witness with 80% accuracy says that a cab was blue when only 15% of them were blue is 41%. So, the fact that the witness said it's blue doesn't even get us up to having our best guess be it was blue, if that's what the base rate is. Because of the weakness of our grasp on the relevance of base rate, we place too much confidence in information about a particular case relative to the base rate for the kind of event we're trying to predict. Information about a particular case is sometimes called individuating information. This gets us in big trouble when that information is fallible. But even when people know the information is fallible, they tend to ignore the base rate. In trials, when the witness points to someone he saw fleetingly at dusk and says, "That's the man," such testimony is usually treated as if it's almost surely true, even when the numbers tell us it's probably false. Well, I'm betting that you made more use of the base rate for the panel truck problem than you did for the cab problem. We're actually pretty good at taking base rate information into account when there's a causal interpretation. When you hear that white trucks cause more than 5 times as many accidents as yellow trucks, this creates an image of hellions behind the wheel of white trucks playing bumper cars in the city streets, and we don't forget that when the witness says that the offending truck was yellow. Now we'll look at a problem that will deal with some pretty familiar-seeming events. A college senior that we'll call David L. was admitted to 2 colleges. One was a large public university, and one was a small private college. The 2 schools were about equally expensive, equally selective, and about equally far from home. David had several friends at each college. His friends at the large university liked it. They found it intellectually stimulating, and they had good friends there. His friends at the small college were not so happy. They didn't find it a very stimulating place to be, and they weren't crazy about either their teachers or their fellow students. David went to both schools for a day. At the large University, he was given the brush off by a couple of teachers he wanted to see. The students he met didn't seem terribly interesting, and he just didn't like the feel of the place. At the small college, he met several students who were bright and fun to be with, a couple of professors who took a personal interest in him, and he left feeling upbeat. Which school do you think David L. should attend? Why? The great majority of University of Michigan students with no statistics say he ought to go to a small private college. And why is that? Well, because he's choosing for himself, not his friends. Can you think of a principle that might suggest this reasoning is dubious? I hope you're thinking about the law of large numbers. His friends have spent scores, if not hundreds of days at their school. He spent one day. His sample size is one compared with hundreds for the total for his friends. We know that sample values can be pretty far from population values if they're small. And intuitively, you know you could meet a few atypical students and encounter a few atypical professors. And you might be off your game. You got a cold or a spat with your parents. The whole college might be a bit off. Maybe it's a particularly bleak day during exam time. On the other hand, maybe the school just won the playoff in basketball. And it's true, he's not his friends, but, and now I'm going to tell you one of the most important things a social psychologist can tell you. And that is, if you're like most people, then like most people, you think you're not like most people. But you are. If everybody you know liked the movie, odds are strong that you will too. And by the way, your friends are not most people. They're people you selected as friends partly because of shared interests and values. So your sample of friends is biased to be more like you than most people are. And that bias means you should be heavily influenced by their experiences. In short, David L. has extremely good base rate data. The first-hand information David L. has could be misleading. Just for interest's sake, I'll tell you that I actually live by base rates. Some of my friends think I'm a little far gone on that, but I don't judge books by their cover. I basically don't read books unless they've been highly recommended by people I trust. Same is true for movies. And let me tell you about how I made my decision to come to the University of Michigan. I was at a school on the East Coast, a good school, and I was asked by folks at Michigan, would I come to interview? Everything I knew about the University of Michigan and the psych department there and the city of Ann Arbor was good. And I made up my mind to go if I got an offer. And I made up my mind not to let myself be influenced by the visit. And a good thing, too, because my visit happened in a February, very cold, patchy, dirty snow on the ground. The chairman and his executive committee spoke mostly about baseball during my interview. The dean obviously didn't hear a word I said. One of the least interesting and pleasant people in the department monopolized my time. Fortunately, I stuck to my guns and went to the University of Michigan. And as it turns out, I actually never heard the word baseball again. Football is a different matter. No baseball. And I found out that the dean was in the midst of an incredible student crisis. There was a demonstration that was feared it would become violent. So it's hardly surprising that the dean was not mentally present. And I was able to avoid pretty easily that guy who wasn't so interesting and pleasant. I want to make one last useful point about base rates for you. In July 1997, the proposed new Scottish Parliament building was estimated to cost £40 million. 2 years later, the budget had become $109 million. That estimated cost increased twice in 2002, ending the year at £295 million. It rose 3 times more in 2003, reaching £375 million. The building was finally completed in 2004 way behind schedule at a final cost of $431 million. A 2005 study examined rail projects undertaken worldwide for the 30-year period beginning in 1969. In more than 90% of the cases, the number of passengers projected to use the system was overestimated. Even though these passenger shortfalls were widely publicized, forecasts did not improve over those 30 years. On average, planners overestimated how many people would use the new rail projects by 106%, and the average cost overrun was 45%. There's no evidence that changed over the course of 30 years. Rail planners didn't bother to take into account this dismal base rate. Well, you might say those are government projects, and even government's biggest fans don't tend to praise government for timeliness or thriftiness or efficiency of planning. How about ordinary citizens? How do they do at planning projects? How well do you think most Americans do in estimating the cost of kitchen remodeling projects? Do you think they overestimate and they're pleasantly surprised at how little of the kitchen cost? Maybe they hit it on the nose or underestimate by 10%, 30%, 50%, 70%. A survey of homeowners who had remodeled their kitchens found that on average they had expected the job to cost $19,000. In fact, they ended up paying an average of $39,000. They underestimated by more than 100%. Well, how about you and me? Do the papers and reports that you write get produced in the amount of time that you anticipated? Mine don't. Why not? I sit down and look over my notes and plans and carefully estimate how much time each part of the project will take. I say, let's see, the introduction just covers standard stuff I've done before. A half day is enough. Methods are always a breeze to write, let's say a day at most. Results could be a little tricky. There are some things I don't know exactly how I'm going to handle. Let's say a day and a half. And then discussions they're never a big deal. They're never very long. So I'm going to say 3.5 days, 4 days tops. And how long does a paper usually take after those calculations? 9 or 10 days, if I'm lucky. So what am I doing wrong? I'm just paying attention to the things I know have to be done, and I can't see around the corners to the myriad little things that are going to crop up. I can't find that reference by Snerdley. My colleague never finished one of the analyses, and I don't know how to do it myself, really. In short, I pay attention only to the individuating information about this particular case, and I'm never going to see all the things that produce delays. So how could I do better? Pay attention to my own base rate for paper writing projects. At the very least, after I do the calculations and come up with the estimated time, I should triple it. Do I do this? Not really. I usually just say vaguely that I'm often surprised, so I realize it might take longer than I think, but secretly, I think this time will be different. It usually isn't. So do what I say here, not what I do. I have learned about other people's foibles. When a tradesman says a project will take 2 days, I triple it in my mind so that I won't be unpleasantly surprised. When I set deadlines for other people, I make them a week or two earlier than I actually need the job done, so I'm not likely to be caught in a bind. Now that should be as easy for you as it is for me. Set deadlines for other people with an eye to your safety and convenience. The next lesson is on cognitive biases. That's the mental procedures that we use to understand the world, and how those procedures can sometimes go awry. Hi, welcome to Lesson 6, which is going to be about cognitive biases. Psychologists and philosophers have discovered a large number of biases that people have, which produce errors. Not all biases are bad, by the way. Bias just means inclination or tendency. And the biases that psychologists are interested in usually promote accurate perception of the world. But we usually mean mistaken or unfair when we say that someone has a bias. And this is a course on critical thinking, so I'm going to talk about biases that sometimes or even usually produce errors. One of the most profound cognitive biases is the illusion of objectivity. This is the belief that we understand the world by direct perception, whereas in fact our understanding of even the simplest thing is guided by layers of cognitive processes. Philosophers call this error naive realism. In other words, we think we've got the real world in a clear, direct way, and that belief is naive because it's not true. Every belief about the world is achieved via a huge overlay of cognitive processes operating on the raw material of perception. These mental processes themselves have underlying biases. Those biases make us inclined to view the world in particular ways. And most of the biases help us to understand the world correctly most of the time. Please take a look at this pair of tables. It's obvious that one of these tables is longer and narrower than the others. Obvious, but wrong. The two tables are exactly the same size and shape. So why are your eyes deceiving you? They're deceiving you in a good cause. Your perceptual apparatus, lens, retina, optic nerves, and the part of the brain where the image is projected and processed are designed to help you see the world as it is. The higher order visual processes, the ones in the brain back behind the retina, operate so as to increase the apparent size of things that are far away. If they didn't, we would see things far away as being much smaller than they are. The perceptual system is trying to achieve what's called size constancy. Our brains doctor the evidence so that things known to be far away seem larger than the image on the retina. That's crucial in the real world. But those tables are not the real world. They've been drawn so that our perceptual machinery decides for us that we're looking at the end of the table on the right and the side of the table on the left. This has the effect of lengthening the table on the right and broadening the table on the left. When you see a table in real life, the adjustment the brain makes to the appearance of the image on the retina is a distortion of what's actually there, but that bias helps us to see the world as it is. But in an artificial world, that same biased operation can cause us to make errors. Not until the 20th century was it understood that perception has as much to do with programs in the brain as with images on the retina. Please read about a fictitious person named Howard. Howard spent a great amount of his time in search of what he liked to call excitement. He had already climbed Mount McKinley, shot the Colorado Rapids in a kayak, driven in a demolition derby, and piloted a jet-powered boat without knowing very much about boats. He had risked injury and even death a number of times. Now he was in search of new excitement. He was thinking perhaps he would do some skydiving or maybe cross the Atlantic in a sailboat. By the way he acted, one could readily guess that Howard was well aware of his ability to do many things well. Other than business engagements, Howard's contacts with people were rather limited. He felt he didn't really need to rely on anyone. Once Howard made up his mind to do something, it was as good as done, no matter how long it might take or how difficult the going might be. Only rarely did he change his mind, even when it might well have been better if he had. So, does Howard seem to be an attractive, adventurous sort of person or an unappealing, reckless sort of person? If several minutes before you read that paragraph you had been exposed to words like self-confident, independent, persistent, you would likely have rated him as an attractive, adventurous sort of person. Those words conjure up what's called a schema or a template. In this case, a schema of an active, exciting, interesting person. If instead you had read words like conceited, aloof, stubborn, you would likely have rated him as an unappealing, reckless person, because that set of words call up a schema of an unpleasant person concerned only with his own pleasures and stimulation. Would you believe me if I told you this man was a high-powered Manhattan lawyer who plays polo and hangs out in trendy bars? No, I didn't think so. The picture instantly conjures up a schema or stereotype of a person who doesn't remotely resemble a high-powered Manhattan lawyer. Schemas are cognitive structures that guide our understanding of the world, usually making us perceive things more accurately than we would without them, and prompting us to behave more appropriately. We have schemas for house, family, Civil War, insect, introvert, party animal, policeman, doctor, fast food restaurant, fancy restaurant. We should behave differently toward a policeman than toward doctors, and we should behave differently in fast food restaurants than in fancy restaurants. So these kinds of schemas are mostly useful, though of course they can lead us astray. Stereotypes in particular can get us in trouble. Schemas can be triggered by very impoverished stimuli, events that we're scarcely aware of. Have a look at these coconuts. If you placed one of them on a shelf above a coffee urn in an office with an honest box next to it, you would get many contributions. Which of those do you think would get more contributions? To give you a hint, coco is Spanish for head. The coconut on the left calls up the schema for a human face. And if there's someone watching me, I want to seem to be honest. You actually don't even have to have something that looks as much like a head as a coconut. Just having a poster with 3 dots in the pattern on the coconut on the left is enough to trigger the schema for a face and get more contributions. People are more likely to vote for increased taxes for education if the polling place is a school. That brings up all kinds of schemas about school and studying and the importance of education. And people are more likely to vote against abortion if the polling place is a church. Makes you conscious of the sacredness of life. Believe it or not, if you have someone read a persuasive communication in a room where there's a fishy smell, the person is less likely to believe it. This seems fishy to me. This only works, by the way, in countries where fishy means dubious. In Denmark, it's a rat that you smell. The fish trick doesn't work there to make people less persuaded. If you want someone to like you, hand them a cup of coffee. They will perceive you as warmer, and avoid iced tea at all costs. I hope all this makes the point that schemas are ubiquitous. They often operate completely unconsciously. They usually help us to understand the world, to behave differently toward policemen than doctors, and to behave differently in McDonald's than in a fancy restaurant. And schemas sometimes intrude in a way that's irrelevant or unhelpful. Schemas shape not just perception, but also memory. In one study, students watched a video of a husband and wife having dinner together. Some of the participants were told that the woman was a librarian, and some were told that she was a waitress. Then after seeing the videos, the students were asked a number of questions about what they'd seen. If they thought they had seen a librarian, they tended to remember she had been drinking a glass of wine. If they thought she was a waitress, they tended to remember she had been drinking a glass of beer. If she was a librarian, they remembered her mentioning a history book. If she was a waitress, they remembered her mentioning a romance novel. So schemas have a profound effect on what we see, what we hear, what we remember, and what we behave, and how we behave. Schemas usually help us to perceive the world as it is, but right or wrong, it's always schemas operating on raw sensation that determine what we see and believe. When political convictions are involved in what we see, we're particularly subject to erroneously believing that we're seeing the world as it is. Social psychologists have conducted a study in the immediate aftermath of a particularly horrible event in the long, tragic history of the Israeli-Palestinian conflict. This was the 1982 massacre of civilians in refugee camps on the outskirts of Beirut by Christian Falangist gunmen. Israelis had some political ties to the Falangists, who were in conflict with various Muslim groups. The question was how fair the media coverage of the massacre seemed to different constituents. In particular, Stanford University students, some of whom were pro-Israeli and some of whom were pro-Palestinian. Both groups were shown the same samples of coverage by the major news networks, and they were then asked about what they had seen. Both saw the coverage as decidedly biased in favor of the other side. In fact, not a single one of the 68 pro-Israeli participants thought the coverage was as favorable to Israel as any of the 27 pro-Palestinian participants did. Moreover, and this is what's really important, both groups came away convinced that nonpartisan viewers would become more favorable to the other side as a result of what they saw. What this means is that since people tend to think of their own understanding of events not as a take, but as a direct, accurate readout of what's going on, anyone who tries to offer an even-handed account of events will tend to be seen as biased and hostile to their interests. Right-wingers in the U.S. talk about the lamestream media, who can't be trusted, and people on the left are angry that the major news outlets maintain what they regard as a mindless neutrality by giving the same coverage and treatment to extreme right views as to the sensible, much more centrist views offered by their side of the political spectrum. And in general, people who see the world as radically different from the way we do are stupid, crazy, or hopelessly biased by their wrong views of the world. If my belief was wrong, I wouldn't have it. So if your belief is different from mine, it's wrong. The comedian George Carlin used to ask his audience, "Did you ever notice that someone driving slower than you is an idiot, and everyone driving faster is a maniac?" In the next segment, we'll talk about what's called heuristics, mental tools that we use to understand the world. So another type of mental tool that we rely on to make sense of the world is what have been called heuristics. These are informal cognitive procedures for solving a variety of everyday life problems involving inference and judgment. They are mental shortcuts or rules of thumb that provide generally useful answers to judgment problems. One of the ones that we'll talk about is the availability heuristic. That assesses how readily certain instances come to mind that's used for judging the frequency or probability of some type of event. And the representativeness heuristic, which categorizes something by how similar it is to our conception of the typical member of the category. It's used for judging probability and for inferring causality by assessing how similar an effect is to some possible cause. Which of these American states do you think has more tornadoes each year? Nebraska or Kansas? Bet you want to say Kansas, don't you? Never mind that the tornado you're thinking about never happened. Most people, though, do think there are more tornadoes in Kansas. The ready availability of a Kansas tornado, which happens to be fictional, makes us intuitively feel that there are more tornadoes in Kansas. And by the way, there aren't, about the same in both states. The logic behind the availability heuristic, such as it is this. If I can quickly recall some, there must be a lot of them. If I can't come up with things very easily, there probably aren't so many. That gives the right answer for whether it's Russia or Norway that has produced the more famous novelists. It also works for which country has started more wars of aggression, Germany or Switzerland. But are there more words with R in the first position or in the third position? Most people say the first position. It's easier to come up with words with R in the first position because one of the ways we store words in memory is by their first letter. We don't store words by their third letters. In fact, however, there are more words with R in the third position. Are there more suicides or homicides in the U.S.? It's easier to come up with homicides, isn't it? And most people think there are more homicides, but suicides outnumber homicides 3-2. Do more people die in fires or drownings? It's easier to come up with fires, but in fact, there are more drownings. Does it seem to you that the rate of crime has increased or decreased in recent years? No matter what's happening to the crime rate, people usually say it's increasing. There are always lots of crime examples available to us. Easy to think of crimes. Must be getting worse. In fact, crime decreased more or less steadily for the 25-year period from 1990 to 2015. Most people thought it was increasing during that period. Notice that the availability heuristic makes us overestimate our contributions to joint projects. The stuff I did is more available to memory than the stuff you did. This can be a source of conflict in many kinds of relationships, including marriage. In one study, married couples were asked how much they contributed to various projects, how much, for example, they contributed to breakfast. The woman said, I contribute 100%. I buy the food, I cook the food, I set the table, I clear the table, I clean the dishes. And the husband said, I do 25% because I feed the cat. Please read the following description. Linda is 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. Which of the following seems more likely? Linda is a bank teller, or Linda is a bank teller who is active in the feminist movement? We'll talk about Linda a little later. Recall that the representativeness heuristic is used for categorizing something by how similar it is to our conception of the typical member of the category, and we use it for assessing causality by judging how similar an effect is to some possible cause. One of the number sequences below is random. The other is not. Which do you think is random? It's the top sequence that's random. It's one of the first two I selected from a random number table. The second one looks more random because it's more representative of a random sequence. It just so happens that our conception of randomness is faulty, which, by the way, gets us in all kinds of trouble. Actual random sequences have too many long strings, 0, 0, 0, 0, 0, and too many repetitive patterns, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. The representativeness heuristic is a perfectly reasonable tool to use to decide whether a pattern is random or not. The problem isn't the mental process, it's the conception of the category that's wrong. If I told you that a student I know is shy and a poetry lover, do you think it's more likely that the person is a student of Chinese literature or a student of business administration? Even on a campus like mine, where you actually can study Chinese literature, there are vastly more business administration students than Chinese literature students. So betting on Chinese literature would be very risky. I'd choose business administration. Lots of them are poetry lovers, I'm sure. Back to Linda, I asked you to read about. If you said she's more likely to be a bank teller who is active in the feminist movement, you're in good company. 85% of college students say that, but it's logically impossible. A and B can't be more likely than just A by itself. The problem shows how powerful the representativeness heuristic can be. A bank teller who is active in the feminist movement is much more representative of someone like Linda than just being a bank teller. But there can't be more feminist bank tellers than bank tellers, or more female bank tellers than bank tellers, or more redheaded bank tellers than bank tellers. So, returning to the last lesson on prediction, why do we tend to ignore base rates in favor of individuating information about an object or person? Partly because we apply the representativeness heuristic so easily to the individuating information. Interviews are compelling because we convert the information we're getting into a stereotype of some kind, a category or set of categories. Go-getter, good sense of humor, solid judgment probably. The base rate information, the information about the person's history of achievement, is pale in comparison to our vivid image of a person that we can classify so easily by using the representativeness heuristic. A number of years ago, I was talking to a friend from graduate school about how successful our fellow graduate students had been in their research careers. As we thought about these people, we began to realize that we were awfully surprised about a lot of them. Some of them did much better than we thought. Some did much worse. So we began to say, well, what were we basing our predictions on here? And it became clear that the basis was how representative our friends were of our stereotype of a good psychologist. Verbally clever, knowledgeable, insightful about people. And then we began to think, what could we have based our judgment on? Could we have done better? And then we realized, yes, we could. We should have looked at the base rate for the person. The more good research they did in graduate school, the more good research later in life. And this reminds me of one of the most useful things a psychologist can tell you. The best predictor of future behavior is past behavior. You're not going to do better than that. No other information you can get is likely to be a better predictor. No amount of interviewing, no psychological test you can give, no promises on the part of the person that they're turning over a new leaf. It's past behavior that you want to pay attention to. The representativeness heuristic is often used for making causal judgments. Causes should be representative of effects with respect to their size. The world changed when Lee Harvey Oswald killed JFK. I don't know whether Oswald acted alone or not, but I do know that the conviction that many people that it had to be a conspiracy was fueled by the sense that he was too small a cause for such a gigantic effect. There must have been a large conspiracy. There used to be a medical principle that diseases could be treated by something that resembled the disease, or something that resembled the opposite of the disease. Jaundice turns people yellow, so you should treat jaundice with yellow things. The lungs of a fox, which has great respiratory powers, can be used for respiratory illness. The representativeness heuristic is the basis for many home remedies that are still in use. In the next segment, we'll be talking about two particular kinds of errors which are very broad in general and which can get us in a lot of trouble. Now I'd like to talk about a particular error in reasoning that is one of the most common errors we make and one of the most troublemaking. When we try to figure out why an object or a person behaved in some way, we're prone to a dispositional bias. That's an inclination to see behavior as caused by dispositions, such as traits, rather than as a response to contexts or situations. This bias routinely causes us to make the fundamental attribution error. which is the tendency to mistakenly regard dispositions of the object or person as the primary cause of behavior while ignoring important situational or context factors. Dispositions include traits, abilities, attitudes, and motives. In one famous experiment, a very long time ago, psychologists asked one group of college participants to read an essay in favor of Castro's Cuba, and they had another group read an essay opposing Castro's Cuba. The first group was told that a political scientist instructor told the students to write an essay in favor of Cuba. And the second group was told that the political science told the student to write an essay opposing Castro's Cuba. Logically, participants should not have felt that they had learned anything about the participants' true attitudes. But in fact, participants who read the favorable essay assumed that the student who wrote it was, in fact, in favor of Castro's Cuba, and those who read the unfavorable essay assumed that the student who wrote it was opposed to Castro's Cuba. In another classic study, students participated in a study with a TV quiz format. One student was assigned at random to be the questioner, and one was assigned to be a contestant. The questioners took advantage of the esoteric knowledge that they had that they could assume was probably not known to the contestant. For example, what is the sweet-smelling, waxy stuff that comes from whales and is used as a base for perfume? That's ambergris, in case you haven't recently read Moby Dick. You might think that it would have been clear to both participants and observers that the questioner had a big advantage by virtue of his role, which meant that he could display some impressive knowledge and couldn't be shown to be ignorant of anything. But in fact, both the contestants and observers who watched the quiz take place rated the questioner as far more knowledgeable than either the contestant or the average university student. The study has profound relevance to everyday life. An organizational psychologist set up a laboratory version of an office. He randomly selected some participants to be manager and others to be clerk. The managers read manuals on supervisory responsibilities, while the experimenter showed the clerks the mailboxes, the filing system, and so on. After the office had been in operation for a while, managers and clerks rated each other on a number of work-related traits, including leadership, intelligence, motivation for hard work, assertiveness, and supportiveness. For all of those traits, managers rated their fellow managers more highly than they rated their clerks, and clerks rated their managers higher than they rated their fellow clerks. And note that these findings were obtained despite the fact that everyone knew that the roles had been assigned at random. In everyday life, people usually can't assume that. So it can be even harder to separate the effects of roles from the dispositions of the people who occupy the role. Notice how the representativeness heuristic, the failure to appreciate the law of large numbers, and the fundamental attribution error operate together in generating our mistakes about how much we can learn from observation of a single behavior. Jan gave the panhandler $1. That's an act that's representative of generosity, so she must be a generous person. I don't pay much attention to the context, which may have been one in which most people would have given the panhandler $1. And I don't do much checking against other behavior by Jan. There's no recognition that a single act doesn't constitute a great deal of evidence. These kinds of powerful biases operating together help to account for our massive failure to appreciate how little we actually learn from a single behavior. Remember an earlier session on correlation and one on law of large numbers? People are very badly calibrated. We asked people what they thought the correlation was between how honest people were in one situation and how honest they were in another, or what the correlation was between how friendly people are in one situation and with how friendly they are in another. People thought those correlations were about 0.8. Huge. In other words, a very, very strong correlation, so strong that we could be reasonably sure that if a person was honest in one situation, he would be in another as well. In fact, the correlation is extremely low for all kinds of traits: honesty, friendliness, aggressiveness, conscientiousness, etc. Predicting one behavior from another that measures that same trait is a risky business. The correlations are quite low. So the fundamental attribution error is very fundamental and very profound and very troublemaking. The last bias that I want to talk about is the confirmation bias. When testing hypotheses, we tend to look only for evidence that could confirm the hypothesis and not for evidence that could disconfirm it. The search for evidence that might disconfirm a hypothesis is as important to testing a hypothesis as a search for confirming evidence. Recall the 2x2 table, where you were asked to decide whether symptom X is associated with disease A, whether it's diagnostic of disease A. Some participants say, yes, it is diagnostic, because some people with the disease have the symptom. They look only at confirming evidence and only at one cell. Other participants say, yes, more people with the disease have the symptom than people without the disease. Those participants look at two cells, but still only for confirming evidence. Very few people understand that all the cells of the table are essential. The evidence as a whole serves to disconfirm the hypothesis. But if you don't look at the evidence that could disconfirm the hypothesis, you'll never discover that fact. Our susceptibility to the confirmation bias means that the way a hypothesis is stated can determine the answer we get. Participants in one study of the confirmation bias were asked to interview someone. Some participants were asked to determine whether the person was an extrovert, and some were asked to determine whether the person was an introvert. The first group was inclined to ask questions for which, if the answer was positive, it would tend to confirm the hypothesis. For example, in what situations are you most talkative? The second group also was inclined to ask questions for which, if the answer was positive, it would tend to confirm the hypothesis. For example, in what situations do you wish you could be more outgoing? Of course, people asked the first type of question are going to appear to be more extroverted than people asked the second type of question. And in fact, when the interview tapes were played for a new batch of participants, those participants judged that interviewees tested by someone who was trying to determine whether the interviewee was an extrovert rated the interviewee as more extroverted than did participants who rated interviewees tested by someone who was trying to determine whether the interviewee was an introvert. You might find that you can use this rule for all kinds of things. Whenever you want to know whether X is associated with Y, or X causes Y, or X is a symptom of Y, think of the 2x2 table. X, yes or no, Y, yes or no. And remember that if you haven't got a number in all four cells, you don't have the ability to assess the question. Psychologists have come up with dozens of biases, and a lot of them are worth thinking about. The ones we've just been talking about are some of the most important, because the consequences can be pretty severe. We can get in big trouble and big arguments by failing to realize that our understanding of the world is an interpretation, not revealed truth. Some of the most important tools we use are schemas and heuristics, which are generally useful, but far from foolproof. And some of the most consequential errors we make are due to our susceptibility to the fundamental attribution error. Finally, many of the inferences we make about the world can be regarded as tests of hypotheses, Unfortunately, too much of the time we simply confirm our hypotheses rather than actually testing them. The next lesson will be concerned with choice, how we can choose between two or more courses of action and what's the best way to do so. Welcome to Lesson 7 on Decision and Choice. We'll be talking about how people make choices and how they can make them better. The first person we know of who tried to devise a systematic way to make people's choices better was a 5th century BC Chinese philosopher named Mo Tzu. But he was a couple of thousand years ahead of his time and a continent away from where he might have had the most impact. He's most famous for developing a theory of logic, and he invented what we'd call today cost-benefit analysis, a procedure where you spell out the possible courses of action, you note the possible costs and the possible benefits of each action, and you choose the action with the best pattern of benefits versus costs, which we call the best net benefit. Mo Tzu's work faded from view in China. Neither his logic system nor his cost-benefit analysis held people's interest there. The next famous thinker that we know of to propose a formal cost-benefit analysis was the French philosopher Blaise Pascal. In the process, he also invented what's come to be called a payoff matrix and the theory of cognitive dissonance. Pascal wanted us to think about whether to believe in God this way. If God exists and we believe in him, the reward is eternal life. If God exists and we do not believe in him, the consequence is eternal damnation. If God does not exist, but we believe he does, the loss is slight, maybe giving up some guilty pleasures and selfish behavior. If God does not exist and we believe he does not exist, the gain is also slight, mostly being able to indulge in those selfish behaviors. I will make a point about Pascal's signs here. He probably got them reversed, not that it's important because it's not a big deal, but there's evidence that unselfish people are actually happier than more selfish people. And if you manipulate somebody into doing something nice for someone else, it makes them quite happy. Pascal realized that this matrix, this 2x2 table, is not going to convince you. You can't just grunt and produce belief in God. In his solution to this problem, he invented the theory of cognitive dissonance, one tenet of which is if our beliefs don't fit with our behavior, this produces mental pain. Something has to change, either our beliefs or our behavior. We don't have direct control over our beliefs, but we do have control over our behavior. So Pascal said, start to behave as if you believe. Taking holy water, having masses said. What have you got to lose? We would say today that he got it just right. Change people's behavior and their hearts and minds will follow. The next installment on what we call decision analysis came from Benjamin Franklin. He pointed out that making a decision can be difficult because, as he said, all the reasons pro and con are not present to the mind at the same time. To get over this, I divide a sheet of paper by a line into two columns, writing over the one pro and the other con. I endeavor to estimate their respective weights. Where I find one on each side that seem equal, I strike them both out. When each is thus considered, separately and comparatively, and the whole lies before me, I think I can judge better and am less able to take a rash step. This basic procedure has been elaborated quite a bit over the years. Economists say that for a decision of any consequence, you should choose from the set of possible actions the action that has the greatest net benefit, benefit minus cost. Since Franklin's time, there have been successive revisions and amplifications of this procedure. Here's a description of the steps that would be endorsed by a decision analyst for an important decision such as which of 3 cars to buy. This is called a weighted decision analysis. So you first list the features that are important to you, cost, gas mileage, and so on, put them into a table, and then you rank order how important each feature is to you, and you assign a weight to each feature based on its rank. So out of 100 points, cost is the biggest one. That gives 35%. Color is not terribly important. You weight that only 0.05. And you grade each option on each dimension. So car A is very cheap, so it gets 9 out of 10. Car C is most expensive, so it gets a 3, and so on. Then you compute each option's score. You multiply its score on a given dimension by that weight, do that for each dimension, and sum up all the numbers for that option. Turns out it's car A. But maybe this is too simple. Who said you should limit what we call the choice space to 3 cars? How about a Mazda or a Volkswagen or a Ford? Should you cast a wider net? And did you really look at every aspect of the 3 cars you're considering? The repair record, the trade-in value, the capacity of the trunk? How many reviews did you read? You could make a minor career out of making this choice, and I have friends who've practically done that. And that's called trying to optimize your choice, getting the absolute best choice, and you need lots of information to do that. But it's sometimes not realistic, just too much information about too many options. The economist and psychologist and computer scientist Herbert Simon said, actually, it's often not rational to optimize. It's better to do what he called satisfice, which is a combination of the words satisfy and suffice. You should spend time and money in proportion to the importance of the decision. Now, that amendment is surely correct as far as it goes as a prescription, but it's actually not a very good description of how people actually behave when you go out into the wilds and see what they're doing. People can spend more time shopping for a shirt than for a refrigerator. They can spend more time pricing barbecue grills than shopping for a mortgage rate. And I am guilty of spectacularly poor calibration of choice time in relation to choice importance. And most professors are guilty of the same thing. The most important decision that professors ever make, the most important financial decision they ever make, takes about a minute. And here's the way it goes. After they've been hired, they visit the department administrator, and one of the questions that he or she asks is how do you want to allocate your retirement investments as between stocks and bonds? What do most people do? Well, most people do 50-50. Oh, that's what I'll do. Now, over the past 70 years, that policy would leave you with much less money than if you put everything into stocks. But I remind you again, I'm not a real financial planner, so you should do some homework if you're confronted with this kind of decision. Maybe the most important modification to Franklin's list that's been proposed is to take probabilities of various outcomes into consideration. When there's uncertainty, you have to do something called calculate the expected value. So let's say you've got 2 job offers, one at Fancy Pants and the other at Smarty Pants. Both stores have great clothes and you like the atmosphere. At both stores, your income would depend on how much you sell. So here's how you would calculate the expected value for a job where how much money you make depends on whether you meet the sales target or not. For Fancy Pants, you get $700 if you meet the sales target. But you're not 100% sure you can meet it. Pretty sure. So you say a 90% chance. At Smarty Pants, the sales target is higher, and you're not sure you can reach it. Not at all sure. So you say maybe a 20% probability that you could reach it. Then you multiply the value of each outcome by the probability of each outcome to get the expected value of each job. And turns out, fancy pants wins. But that wouldn't necessarily have been obvious to you if you hadn't done a formal expected value analysis. Now let's consider an extremely complicated and consequential choice that a friend of mine actually had to face. He was a professor at a very good university in the Midwest and was invited to go to a very good university in the Southwest to start a new center for a new field of medicine that he had founded. No such center existed. The alternative actions were to go or stay. The affected parties were my friend, his wife, their grown children in the Midwest, potential students and faculty at the center, and the world's people at large, because probably that field of medicine would be more widely used and drawn upon if there were a center for it. Some of the benefits are easy to identify. Starting a new center and advancing his field, escaping Midwestern winters, higher salary, change of intellectual scenery, but the impact on the world, hard to assess. And the probabilities of some of these things, not so easy. Some costs are easy to identify and assign weights to, but hard to assess the probabilities for. So hassles of moving, who knows? Burdens of administration, could be a snap, could have a great assistant or maybe not. Leaving treasured friends and colleagues, hard to know how important that's going to be. The costs and benefits for my friend's wife were similar to those for him, but fewer costs and benefits that needed to be calculated because her occupation was novelist, which is portable. In measurement, money works for salary, but how much money is it worth to have a January day of sun and 60 degrees versus clouds and 20 degrees? How much is the estimated pleasure of setting up a new center offset by the aggravation of recruiting staff for it and administering it? So why bother to do a cost-benefit analysis at all in this wildly complicated situation? Because, as Franklin said, your judgment will be better informed and you'll be less likely to make a rash decision. There's one more very important thing to say about decision-making. I have a friend who once had to make a decision. It's very important. It involved both her love life and her work life. And so she sat down to systematically plot all the costs and benefits. And as she's finishing up, she says, "Oh, darn, it's not working out. I have to come up with some more benefits for choice B." And there was her answer. The decision her analysis was pointing toward was not the one she was discovering that she truly wanted. Pascal said, "The heart has its reasons of which reason knows nothing." And Freud said, "When making a decision of minor importance, I've always found it advantageous to consider all the pros and cons." In vital matters, however, by which he meant love and work, the decision should come from the unconscious, from somewhere within ourselves. So my friend's heart quite properly overruled her head, but the heart is also influenced by information. And the unconscious does indeed do a lot of the work. As a matter of fact, there's increasing evidence that the unconscious mind can make some kinds of decisions better than the conscious mind. In any case, it's a qualitatively different kind of analysis that goes on in the conscious mind and the unconscious mind. So for the most important decisions, my advice is do your homework, list your pros and cons, then throw the worksheet away and sleep on it. In this next segment, we're going to discuss some surprising implications of cost-benefit theory that many people are unaware of. Let's consult your inner economist on a few problems. Did you ever walk out of a restaurant without finishing a meal because you didn't like it? Would an economist say that was a wise thing to do? Suppose you intended to go to the theater. The ticket had cost $50, but as you walk up to the entrance, you discover you lost the ticket. Would you buy another ticket for $50, thereby paying $100 in total? What would an economist say to do? A hospital in your town is about to be torn down to make way for a new one. It would cost about as much to renovate the old hospital, which had been extremely expensive to construct, as to build a new hospital. Would you favor renovation or construction? What do you think an economist would say? Suppose last month you paid $80 for a ticket to a basketball game in a city 45 minutes away from where you live. But tonight's the night. The Star is not going to play. Nothing hangs on the outcome of this game, and it's just started to snow. So what to do? What's the best reason you can think of to go to the game? What's the best reason you can think of to stay home? And what would an economist do? Here's what an economist would do. He or she would say, let's assume you didn't have that ticket for the basketball game. And a friend calls you up and says, hey, I have tickets for the game tonight. I can't use them. Can you? If your answer would be, oh, great, I'll be right over, then by all means, go to the game. But if your answer would be, oh, you've got to be kidding, the Star's not playing, nothing hangs on the outcome of this game, and it started to snow, there's your answer in that case. Now, you may feel uncomfortable about not going to that game because that $80 is salient to you, but you shouldn't feel uncomfortable, and you won't in the future in this kind of situation when you become familiar with the sunk cost principle. Only future benefits and costs should figure in your choices. Time and energy and money spent on some activity no longer have any relevance once they're expended. Only if the activity is valued in its own right should it be carried out. If you don't think that way, for the basketball game, you're going to pay twice, once for the ticket and once for the tedium. The sunk cost principle follows directly from the main rule of cost-benefit theory, which is you should always choose the action with the greatest net benefit. That's benefit minus cost, and costs already expended are not included in your cost. That's not legal. The fact that the old hospital in your town was extremely expensive to build is irrelevant to a choice as to whether to renovate it or raise it and build something else. The taxes your grandparents paid to build the old building are long gone. The decision to keep the hospital or destroy it should be made only with respect to the future. So should you eat a lousy meal that you paid a lot for? Not unless you're too poor to buy peanut butter for a sandwich when you get back home. Economists walk out of restaurants with their meal uneaten quite frequently. And they walk out of movies they paid $15 for. And they walk out of athletic events that are turned out to be boring and that they paid $100 for. The economist's motto, and it should be yours, is the rest of your life begins now. 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 So you find you've lost your theater ticket. Should you buy a replacement ticket? By now, I assume you know the answer is yes, unless the value of the play is less than it was when you bought the original ticket. You're not paying $100 for your ticket. The $50 is gone. It doesn't count. You're keeping the books wrong if you think about it. To see this, suppose instead of realizing at the theater entrance that you lost your ticket, you hadn't lost your ticket. In fact, you haven't bought your ticket yet. But you realize you left $50 on the counter in a pizza joint yesterday in another town. would you now turn around and go home rather than buying a ticket? Probably not. So, you see, it's only future benefits and costs that count. It's just as much of a mistake to include the lost ticket into your costs as it would to include the lost $50 bill. Policymakers who are unfamiliar with the sunk cost principle will often try to spend your money to rescue money they've already spent. True, the X-4 bomber isn't very good, but we can't afford to waste the $20 billion we've already spent on it. Wrong. If that $20 billion has produced a substandard product, can it? Drug companies sometimes try to justify exorbitant drug prices on the grounds that they need to recoup the cost of development. That's nonsense. They're going to charge what the traffic will bear, whether the development costs were $1,000 or $100 million. Many years ago, my wife and I bought a summer cottage, and it put us absolutely at the edge of our finances. And we didn't have money to buy furniture. So I decided I'd build the furniture myself. Now, for some people, that would be a quite reasonable thing to do. But not for me, really, because I'm the kind of person, when I was a kid and I built model airplanes, there were always parts left over after I had finished. So I decided I would learn how to make furniture. I'd go to classes. And after 15 hours or so of that class, I had managed to build a box. And it's now dawning on me, this is crazy. I can't make furniture. It's a stupid thing for me to try to do it. It would have been smarter for me to take a part-time job at McDonald's than it would to try to make my own furniture. And there's another extremely important implication of cost-benefit theory. You remember that you should choose the action with the greatest net benefit. But if you don't, you're paying unnecessary opportunity costs. Every action has a cost, namely the net benefit, the benefit minus the cost, of the second best action. Make sure that the second best action really is the second best. If it's actually better than what you were planning to do that instead. But we're constantly paying unnecessary opportunity costs. Economists, not so much. They don't mow their own lawns or wash their cars or clean the windows to their house. There's always something else they would rather be doing. As a British economist said to me once, never do anything you can hire a small boy to do. A person who drives a car rather than taking public transportation is going to be out of pocket for the car, the gas, the maintenance, the insurance, the garaging. That money could have been used for something else valuable, like travel or a housing upgrade. But the cost of using a car on a particular occasion always seems slight. I mean, it cost me 50 cents to drive downtown. Feels like it's practically free, really. And every trip by bus or subway hurts a bit. Oh, $2.75 just to go 12 blocks. A lot of younger people are beginning to realize this, by the way, and not buying cars. Zip cars and the like help people to have this realization. Suppose you owned an office building and you need an office yourself. So you say, well, I'll have an office in my own building. It's free. Actually, an accountant might say it's free, but it's not. If you could get another office just as good in somebody else's building for less money and rent your own out, the one you were thinking you might have, to someone else for more money, you're paying an opportunity cost to keep your office in your own building. My colleagues in my psychology department frustrate me a lot on this issue. Every hire involves an opportunity cost. That's the next most qualified person that you might have hired. And sometimes the mood is, this so-and-so is available. pretty darn good psychologist. We should hire him. And the question that ought to pop into people's mind and doesn't seem to do so often is there someone more qualified than this if we could get if we advertised widely for it? In the next section, we'll talk about two questions. One is, how do we know that the economists are right? And how can we avoid certain financial pitfalls that have been discovered relatively recently by economists and psychologists? If you were to ask an economist, how do you know that cost-benefit theory and its corollaries of sunk cost and opportunity cost are the way to live your life? How do you know that that's the right way to handle your finances and the way you organize yourself? Economists will say, well, it can be mathematically proved from the axioms of cost-benefit theory. And corporations pay for decision analysts. Is that convincing to you? It's not to me. Logical consistency doesn't prove practical utility. And remember, optimizing was considered the thing to do until Simon came along and said, no, it's satisficing you ought to be doing. And corporations do pay for decision analysts, but they also pay for handwriting analysts, lie detectors, motivational speakers to hop around a stage and tell jokes, and they hire on the basis of interviews. What if you knew, though, that the greater your familiarity with cost-benefit principles, the more likely you are to use them? That's including the sunk cost principle and the opportunity cost principle. Well, in fact, I know from research I've done, economists are much more likely to live their lives in line with cost-benefit theory than other professors at my university. Students who've had an economics course do a little better, not much. And as a matter of fact, you've learned much more in this little lesson today than students get from an entire microeconomics course. The text used at my university has precisely one example of sunk cost, and it's not even a very good example. When I teach the principles, and this is important to deciding whether they're right or not, it has an impact on people. I know that because weeks later, I test how they make their decisions in contexts they don't even know they're in a psychology experiment, and it has an impact. And finally, people who report making the kinds of decisions that are encouraged by cost-benefit theory do better in life. At any rate, professors who live their lives in accord with cost-benefit theory make more money. They get higher raises. Students who live their lives in light of cost-benefit theory get higher grades, including higher grades than they should get based on their entrance exam aptitude scores. The overachievers are people who overuse, so to speak, cost-benefit theory. And that makes sense because violations of sunk cost and opportunity cost principles usually involve wasting time or resources. Well, the final topic I want to discuss is some foibles that have been discovered by people who work in a discipline at the margin of economics and psychology. And they've discovered choice and decision quirks that cost money and sometimes even lives. Suppose you need some money and you have to sell one of the two stocks that you own. Which stock should you sell? One that's been going down in hopes that the one that's going up will keep going up? Or one that's been going up so that you won't lock in your losses on the stock that's going down? Most people say they sell the one that's going up. But selling your winners and keeping your losers leads to the poorhouse. Whether you retire rich or not rich, or poor or not poor, depends on making sure that you keep winning stocks and get rid of losing stocks. Suppose that out of the kindness of my heart, I give you $100. And then I say, I'm a betting man. I propose we have a bet here. I'm going to let you toss the coin, and if it comes up heads, you give me back that $100. So you don't have anything. If it comes up tails, you get to keep that $100 I gave you, plus X, some amount of additional money. What would X have to be in order for you to take that bet? Notice that 0 would be fair. That's $100 versus $100. Even $1 would be in your favor. That's $100 versus $101. That's a bet with an expected value of 50 cents, 1/2 times $1. What amount would tip you over to take that bet? $5? $10? $20? The average that people hold out for is $100. If you don't take the bet at $99, you've thrown away $49.50. That's 1/2 times 99. So why do people make these kinds of mistakes? It's because of something called loss aversion. A loss seems to be about twice as painful as the same gain is pleasurable. This causes people to forego lots of opportunities that they shouldn't forego. People pick the wrong stock to sell because if they pick the one that's going up, which they probably know is going to continue to go up, they lose some money for sure. People hold out for a ridiculous amount of money on that $100 bet because the prospect of loss is so costly psychologically. Loss aversion underlies what's called the endowment effect. People demand more money for a thing than they paid for it, often a lot more. Imagine you paid $50 for a ticket to a football game, and a couple of days before the game, tickets are selling for a lot more than their face value. Suppose you see offers of $200 for your ticket on the internet. Would you sell? Maybe not, but you should if the game was worth no more than $50 to you initially, and things haven't really changed. You should be willing to sell that ticket. The following experiment has been done by now hundreds of times in business schools. You give half of the students in the class a mug with the school logo on it, and you ask the other half how much they would pay one of the owners in the room to get their mug. And you ask the owners how much they would demand to sell their mug. Owners demand twice as much as non-owners are willing to pay. So I didn't really care all that much about that coffee mug. And you give it to me now? Oh, that's great. I'm going to keep this thing. And don't try to take it away from me. My university's musical society did a fascinating experiment recently. They advertised the new concert series, and they included in the envelope either a letter with a promo code for $20, saying you can get $20 off the series if you tell people this promo code, or they gave them a piece of paper which said $20 voucher. They got 70% more people buying the concert series with the voucher than with the promo code. So I can tear up that letter, promo code, to heck with it. The $20 voucher, am I going to tear up this $20 voucher? Doesn't seem reasonable. So the bottom line for all of this is, what am I losing to avoid this loss? Just how much do I really want this mug, this soccer ticket? Am I buying this thing just because I got a discount? And retailers should take notice, give coupons, not promo codes. The last topic I want to discuss is what the behavioral economists call choice architecture. you might be surprised to know that only 12% of Germans allow harvesting of their organs for use for other people in the event of their death. 99% of Austrians allow harvesting of their organs. Bet you never would have guessed how much nicer and more generous Austrians are than Germans. Well, actually, we have no reason to assume there's any difference. The difference is that in Germany, you have to check a box if you are willing to donate your organs. And in Austria, you have to check a box if you're not willing to donate your organs. That results in a huge difference in compliance. Or here's another example of the same point. Sometimes when people are hired on a job, one of the forms they have to fill out, they have to check a box if you want the company to contribute money to your retirement account. Or they have you check a box if you don't want the company to contribute to your retirement. That's the difference between 20% people signing up initially and 90%. So how much choice is enough? I have a German friend who came to work in my department, and after he'd been here for a while, he said, "Why do you Americans need 50 kinds of breakfast cereal?" I didn't have an answer. Retailers, at least in America, consistent with good economic theory, give people lots of choice. The Coca-Cola company thinks you want a lot of choices, that's for sure. Which do you prefer? Coca-Cola, Diet Coke, Coca-Cola Light, caffeine-free Coca-Cola, caffeine-free Coke, caffeine-free Coca-Cola Light, Cherry Coke, Coke Zero, Vanilla Coke, Diet Vanilla Coke, Diet Cherry Coke, or Diet Coke with lime, in a green can, by the way. Or maybe you'd really just rather have a Dr. Pepper. There's an upscale grocery store in Silicon Valley which offers 75 types of olive oil, 250 types of mustard, 300 types of jam. And social psychologists set up a tasting table to see, do people really want all this choice? How well does the retailer do with giving people a huge amount of choice versus a small amount? So they set up a tasting table, which either some days had 6 types of jam on it, and other days had 24 types of jam on it. 10 times as many people bought a jar if there were only 6 types of jam at the tasting table. So there are 2 morals here. Don't overestimate people's willingness to consider alternatives. There's a cost to that can result in big losses. In the next lesson, we'll talk about 2 very different approaches to critical thinking: logic and dialectical reasoning. Welcome to Lesson 8, Logic and Dialectical Reasoning. These 2 types of thinking have been around at least since the 5th century BC. They were developed in Greece, India, and China at about the same time. Logic developed in Greece and India in a little bit later than dialectical reasoning, and it remained a strong tradition in those countries, but quickly became unknown in China. So why should you learn formal logic? Because if you haven't had any, you think you'll probably be able to make pretty good inferences without that. I think there are 3 reasons. One is that an educated person should know something about this achievement of civilization. Secondly, it's necessary for science and mathematics. And interestingly, learning science and mathematics teaches you about logic, and logic teaches you to do science and mathematics a little better. And third, it's useful to understand the difference between truth and validity of a conclusion or inference. An argument is valid if the truth of the premises logically guarantees the truth of the conclusion. For example, premise 1, Jane either owns a Honda or a Toyota. Premise 2, Jane does not own a Honda. Therefore, Jane owns a Toyota. A conclusion based on premises can be manifestly nonsensical, but still be valid if it follows the structure of a valid argument. For example, premise 1, Jane either owns Russia or India. Premise 2, Jane does not own Russia. Therefore, Jane owns India. That's a valid argument, although it's complete nonsense. We sometimes accept a conclusion based on faulty logic if we don't have a clear understanding of what the valid logical structures are. We're especially likely to do that if the conclusion is something we want to believe. That's not something you want to do. You don't want to believe something because you think it follows logically from other things you know, if it doesn't. Also, we sometimes reject a proposition that's distasteful to us, even though it follows from the premises, and we have to admit the premises are true. That's also not something you want to do. Formal logic is a type of deductive reasoning, which is sometimes referred to as top-down reasoning. Given the prior inputs, you must accept the conclusion. If you obey the rules, you're guaranteed a deductively valid conclusion. Whether the conclusion is true or not depends on the truth of the premises, the statements that precede your conclusion. Two kinds of deductive reasoning have received a lot of attention historically. One is the syllogism, which consists of categories and quantifications. They typically have a major premise, which is often a generalization of some kind, and a minor premise, which typically refers to an example of the subject of the generalization, and a conclusion which follows from those premises. A classic one, the most common one that people use for an example of syllogism, is all A are B, C is an A, therefore C is a B. With content, also quite famous. All men are mortal. Socrates is a man. Therefore, Socrates is mortal. Has that same structure. It's a valid argument. But you can have a valid argument with that structure, which is, again, total nonsense. All autos are purple. Socrates is an auto. Therefore, Socrates is purple. That is a valid conclusion, although ridiculous. Just to check, make sure that I'm telling the truth, that really is a valid argument. You can see that has the structure here. Try this syllogism. Does it seem to be valid to you? All people on welfare are poor. Some poor people are dishonest. Therefore, some people on welfare are dishonest. Well, let's see what the structure of that argument is. All A are B, some B are C, therefore some A are C. Well, that does not follow. That conclusion isn't dictated by the premises. So there are dozens of forms of syllogisms that have been described over the ages. All A or B, some C or A, therefore some C or B, valid or not. I don't find many of them useful. Amazingly, for centuries, syllogisms comprised a large fraction of higher education in Europe and subsequently in America. They're not. Most people get through their college careers without ever seeing them, and I think they don't suffer much from that. The most useful formalisms for categorical reasoning are so-called Venn diagrams. They're named after the 19th century logician John Venn. They're a pictorial way of representing category membership. Category memberships that are very difficult to understand verbally can be a snap in picture form. So the picture on the left above captures a particular syllogism that we do use in everyday life. Some, but not all A are B. Some, but not all B are A. So some, but not all small furry animals have a bill like a duck. Some, but not all duck-billed animals are small and furry. That's the intersection of A and B, where those two circles meet. And that intersection, of course, refers to the duck-billed platypus, which, so far as I know, is the only duck-billed animal that's small and furry, or small and furry animal that's duck-billed. It can also be used to describe a situation, for example, in which some, but not all of the students who are English speakers at an international school also speak French. And some, but not all French speakers also speak English. The students who speak only English have to study with Ms. Smith. The students who speak only French have to study with Monsieur Poirot. And the intersection represents those students who speak both languages and who can therefore study with either teacher. The picture at the top right shows the complicated but not uncommon situation in which some A are B, some B are A, some A are C, some C are A, some B are C, and some C are B. And here's an actual example of just that kind of Venn diagram. The circle on the left shows all of the letters which appear in the Greek alphabet. The circle on the top right refers to all of the letters which appear in the Latin alphabet, and the circle on the bottom shows those that are found only in the Russian alphabet. This intersection shows the letters which are found both in the Greek alphabet and the Latin alphabet. This intersection shows the letters which are found both in the Greek and Russian alphabet, and this intersection shows the single letter which is found in both the Latin alphabet and the Russian alphabet. And you wouldn't necessarily have known that there are those particular ones at this intersection which are found in all three alphabets. I challenge you to generate those intersections without drawing a Venn diagram. At any rate, I'm sure I would end up with alphabet soup. Other major formal reasoning schemes include propositional logic. This is somewhat more recent in intellectual history and much, much more important than syllogisms. It tells us how to reach valid conclusions from premises. For example, the logic of the conditional. The conditions for a thing to be true are either necessary or sufficient. Sometimes one thing is necessary in order for another thing to be true, and sometimes one thing is sufficient in order for another thing to be true. They're not the same thing by any means. The most common form of conditional logic is modus ponens, which is, you've heard before, if P then Q, P therefore Q. If P is the case, then Q is the case. P is the case, therefore Q is the case. If it snows, schools will close. It snowed, therefore school will be closed. So P is a sufficient condition for Q. It's not a necessary condition because schools could be closed for other reasons. There might be a tornado suspected or an earthquake. Sometimes a given thing is both necessary and sufficient in order for another thing to be true. For example, being a male sibling is a necessary and sufficient condition to be a brother. Being a male sibling is sufficient for being a brother. All you need. And being a male sibling is necessary for being a brother. There's no other way to be a brother except by being a male sibling. So just as for syllogisms, propositional logic has to map onto a cogent argument form in order to be able to yield a valid conclusion. For the conclusion to be true as well as valid, it's also necessary for the premises to be true. The nice thing about premises that are true and form a valid argument is that you have to believe their conclusion, like it or not, unless you have other information from outside the argument that contradicts the conclusion. Decide for each of the following arguments, each having two premises and a conclusion, whether it's valid or not. Premise 1, if he died of cancer, he had a malignant tumor. Premise 2, he had a malignant tumor, therefore, he died of cancer. Please stop the presentation till you've decided whether the argument is valid, and then pick it up with argument B. Premise 1, if he died of cancer, he had a malignant tumor. Premise 2, he didn't die of cancer. Therefore, he didn't have a malignant tumor. Again, stop the presentation till you've decided whether the argument is valid. In argument C, if he died of cancer, he had a malignant tumor. He died of cancer, therefore he had a malignant tumor. Only argument C is valid. It maps onto modus ponens. If P, then Q, P, therefore Q. If cancer, then tumor, cancer, therefore tumor. The plausibility of the conclusions in arguments A and B tempt us to say that they're valid. Argument A, however, maps onto an invalid argument form. If he died of cancer, he had a malignant tumor. He had a malignant tumor, therefore he died of cancer. That's called the converse error because the form of reasoning erroneously converts the premise if P then Q into if Q then P. If the premise had been if Q then P, if tumor then cancer, then we know, in fact, that since Q is the case, P is also the case, tumor, therefore cancer. We make converse errors frequently if we're not monitoring for logical validity. Have a look at this converse error. If the car is not in our garage, then Jane went downtown. Jennifer told me she saw Jane downtown, therefore the car won't be in the garage. Making that error is more likely given some kinds of background knowledge than others. If Jane rarely goes anywhere without the car, then the error is likely. If she sometimes takes the bus and is sometimes driven by a friend, we're less likely to make the error. Argument B was if the person died of cancer, then he had a malignant tumor. He didn't die of cancer, therefore he didn't have a malignant tumor. This is called the inverse error. We invert the premise if P then Q into if not P then not Q. We make this error a lot too. Here's an example. If it's raining, then the streets must be wet. It's not raining. Therefore, the streets must not be wet. If we live in a city where the street sweepers operate frequently, thereby making the streets wet, or if it's a blazing hot summer day in a city where the hydrants are sometimes opened to cool kids off, we're less likely to make the error. If we live in rural Arizona with no street sweepers and no hydrants, we're more likely to make the error. An interesting and important thing to know about the converse and inverse errors is that they only yield deductively invalid conclusions. They can actually be pretty good inductive conclusions. That is, if the premises are true, the conclusion is more likely to be true. It's more likely the car won't be in the garage if I know Jane is downtown. If it's not raining, it's more likely the streets won't be wet. Inductive reasoning is a bottom-up logical process in which multiple premises, all believed to be true, or at least true most of the time, are combined to obtain a conclusion which is deemed probably true. For example, we observe facts and reach a general conclusion about facts of their particular kind. I observe hundreds of swans. They're all white. Therefore, all swans are white, except, of course, that perfectly reasonable inductive conclusion turned out to be wrong. Inductive reasoning is often used for prediction or forecasting, and scientific reasoning nearly always involves inductive reasoning. In fact, scientific reasoning is usually completely dependent on inductive argument forms. All types of inductive reasoning discussed in this course, law of large numbers, regression, statistical significance, and so on, are inductively valid. Getting a larger sample will probably come closer to the population value than if we get fewer. Larger numbers are more likely to get us a right answer, but there's no guarantee. What we've covered in this lesson about deductive reasoning is a tiny fraction of the world of logic. At my university, I'm sure there are a half dozen courses in logic that build on the principles that we've been talking about. But the concepts that we've been talking about today are the most useful ones, I believe. And those concepts are deductive versus inductive reasoning, or top-down versus bottom-up reasoning, syllogisms, which have to do with categories and quantification, conditional logic, if-then statements, for example, modus ponens, if P then Q, P therefore Q, the concepts of necessity and sufficiency, for example, P is a sufficient but not necessary condition for Q, and two types of errors, the converse error, converting if P then Q into if Q then P, and the inverse error, altering if P then Q to if not P then not Q. In the next segment, we'll be talking about a very different kind of reasoning, not so formal and structured as logical reasoning, and as a matter of fact, opposed in some ways to logical reasoning. Dialectical reasoning is at least 2,500 years old. It was independently invented in Greece, India, and China at just about the same time, and it's remained a preponderant way of reasoning in China, while being much less common in countries which are the intellectual inheritors of the Greek and Indian tradition. Socrates taught his students to reason dialectically. In the Socratic dialogue, which was a conversation or debate, people offer propositions and argue for them. Other people add, modify, or contradict those propositions, and the point is to reach the truth about some matter. The next major installment in the West on dialectical reasoning was the 18th and 19th century German philosophers, Kant, Fichte, and Hegel, and their most famous contribution was the concept of matters proceeding by a thesis, followed by an antithesis, something which contradicts that thesis, followed by a synthesis, something which reconciles those two theses. Dialectical reasoning is also the form of reasoning that's characteristic of Talmudic discourse, which has been around again for about 2,000 years, ever since Jews in the Middle East became aware of the Greek dialectical form. The Chinese version developed at the same time as the Greeks. Like the Greek, it was not formal or deductive. The goal is to reach correct conclusions, or even more, to reach useful conclusions. And it's much more concerned with the acceptance of contradiction than getting rid of it. It deals especially with intellectual and social conflict, with uncertainty, and with change. Recently, psychologists have begun to study it, and it's called post-formalism. The great developmental psychologist Piaget said that the formal rules of propositional logic are what constitutes reasoning. That's it. Turns out to be a spectacularly wrong hypothesis. This course has been full of principles of reasoning that don't involve logic at all. The post-formalists, people who are looking at the kinds of reasoning patterns that we develop well after the formal rules, the logical rules have developed, are not deductive. They involve attention to relations and context. They're anti-formalist because of a belief that it's a mistake to separate form from content. And it's very much concerned with identifying contradiction and transcending contradiction, or accepting it, or using the contradiction to learn something new about the world. It's also very much concerned with change and with uncertainty. This is really utterly different from the central Western tradition. It's always been there in the West, but it's never been central in the way that logic has been. The East Asian tradition is much more sympathetic to these kinds of principles than the Western tradition. To show you just how different East and West are in their fundamental assumptions about the way to reason, Aristotle proposed the following propositions as the foundation for logical thought. First of all, identity. A equals A. Whatever is, is. A is itself and not some other thing. Non-contradiction. A and not A can't both be the case. Nothing can both be and not be. A proposition and its opposite can't both be true. And the excluded middle. Everything must either be or not be. A can be true or not A can be true, but not something in between. It might seem that there's nothing to disagree with here, but in fact, East Asian thought disagrees with all these propositions. The Chinese psychologist Kai-Ping Peng has identified the foundations of dialectical reasoning, and he doesn't call them propositions, by the way. They're looser than that. One is the principle of change. Reality is a process of change. What's currently true will shortly be false. The principle of contradiction. Contradiction is the dynamic underlying change. Because change is constant, contradiction is constant. The principle of relationships, or holism. The whole is more than the sum of its parts. Parts are meaningful only in relation to the whole. These principles are intimately linked. Change creates contradiction, and contradiction is going to result in change. Constant change and contradiction imply that it's meaningless to discuss the individual part without attending to its relationships with other parts and with previous states of the world. There's a strong emphasis in Eastern thought on finding the middle way between extreme propositions. Contradictions are often merely apparent. A is right, but not A is not wrong. Now, this way of thinking is not alien to Westerners. We're familiar with all of this. And Westerners have made contributions to the dialectical tradition. But when push comes to shove, Westerners usually side with logic and Easterners with dialectical approaches. By Easterners, I mean Chinese, Koreans, Japanese, among others. As an interesting demonstration of the difference, Peng presented Americans and Chinese with pairs of alleged scientific findings. They're near contradictions. One statement was always more plausible than the other. And they weren't literal contradictions, but if you believed one, you wouldn't be likely to believe the other. So fuel usage in a large number of developing countries indicates a great worsening of environmental problems, including global warming. And the statement, a meteorologist studied temperature in 24 widely separate parts of the world and found that temperatures had actually dropped by a fraction of a degree each of the last 5 years. Some participants saw only statement 1, some saw only statement 2, and some saw both statements. All participants were asked about their beliefs about each of the statements. The Americans actually believed the more plausible proposition, which was the first one here, by the way. Americans actually believed that proposition more when they were also exposed to the less plausible proposition than if they weren't. That's actually logically incoherent, as philosophers would put it. A proposition can't be more plausible if you've seen something contradicting it than if you haven't. In trying to get rid of the contradiction, the Americans beefed up the more plausible proposition and weakened the less plausible one. It was so important to decide which of these things is correct. In complete contrast, Chinese actually believed the less plausible proposition more when they had also seen the more plausible proposition than when they hadn't. This is also logically incoherent. A proposition can't be more plausible if you've seen something contradicting it than if you haven't. In trying to find ways in which both propositions could be true, the Chinese beefed up the less plausible proposition. That can sometimes be useful, but it's not logically allowable. Have a look at a brief video, which is of an underwater scene. And I'm going to ask you, after you've seen that video, to tell me what it was that you saw. Okay, please note, write down if you can, what it was you saw. You'll find that what I'm about to say will be more interesting if you actually do that. This video was shown to Japanese and American participants, and what people reported as having seen was very different. Americans said, "I saw what looked like 3 big fish swimming off to the left. They had pink stipples on their bellies and fins on their backs, and there were rocks and shells and plants on the bottom." The Japanese almost always started with context. They said, "I saw what looks like a stream. The water was green. There were plants and shells and rocks on the bottom. There were 3 big fish swimming off to the left." The Japanese participants actually reported 60% more information about the context than the Americans did, and they reported twice as many relationships. The frog was close to the plant than the Americans did. Easterners pick up much more contextual information in pictures and in movies and in ordinary life situations than Westerners do. And when describing a situation, they emphasize the context information. They begin with it. Then they note relationships among different aspects of the context. A second profound way in which East and West differ is that Westerners believe the world is static. That's a heritage we have from the Greeks. I don't know why it was so obvious to the Greeks that the world was unchanging, but that's what they believed. Or if it is changing or seems to be changing, it does so in a linear fashion. In contrast, Easterners believe the world is constantly changing, often in a cyclical pattern. In fact, the fact that the world is in one state now is just an indication that it's about to be in another state in a bit. This causes Easterners to make decisions like the following. If they're presented with a choice between buying a stock that is increasing versus one that's decreasing, whereas Americans go for the increasing stock, Chinese are likely to go for the decreasing stock, because the fact that it's decreasing just means it's about to be increasing, because change is the nature of the world. That's a mistake, by the way, as I pointed out in the last lesson, to keep or buy a stock that's decreasing rather than one that's increasing. Well, logic has its virtues, but a dialectical approach to problems, especially social problems, can be wiser. Igor Grossman and a number of his colleagues at the University of Michigan presented American subjects and Japanese subjects with social conflicts of various kinds. For those of you who know the genre, we gave them Dear Abby questions, where the newspaper columnist gives her judgment about what should be done in some conflict. So, for example, one of the social conflicts involved a sister and brother in a conflict about how much each should be expected to pay for a gravestone for their parents. And we coded the answers for the avoidance of a rigid application of a rule, for taking into account the perspectives of each person involved, for being attentive to the nature of contradictory views, to recognizing the likelihood of change rather than a stalemate, to mentioning possible forms of compromise, and for the expression of uncertainty rather than undue confidence. The young Japanese were substantially wiser by these criteria than the young Americans. The Japanese, however, get no wiser as they get older. 75-year-old Japanese are not wiser by these criteria than 25-year-old Japanese. Americans start out low, but they do get wiser. And I think these differences come from the fact that Japanese culture teaches how to avoid conflict and how to deal with it if it occurs. Conflict is a much bigger deal, social conflict, in the East than it is in the West. American culture doesn't teach those things all that well, so Americans get into conflicts frequently, and they have to learn ways of avoiding it and dealing with it if it happens. And older Americans are about as wise as older Japanese. So which is better, logical thinking or dialectical thinking? I'm sure you think that what I think is that that's not really a sensible question. They serve different purposes. When it's really necessary to discern the nature of an argument, or to be sure that a conclusion follows from what you already know or assume to be true, you really do need logic. Logic is also extremely useful for rhetoric, for convincing other people. In scientific papers, I'll often put what for me were loose arguments, I put them into a rigid, logical form because it helps to convince other people. It's a rhetorical tool. Sometimes when you put what you think you know into a logical structure, this can force you to realize you actually don't have a logical case, which is quite useful. When you're trying to understand something from a variety of perspectives, or when you're trying to avoid or solve social conflict, dialectical reasoning is what's called for. Well, that's it, except for a wrap-up that follows this session. Well, I hope you've enjoyed the Mindware course as much as I've enjoyed working on it. And I hope you agree that you're smarter now. Not only have the tools in the course made you smarter, but they're the kinds of tools that sharpen themselves. This is not like many of the courses you've taken where the last day of class is when you're most on top of the material. Every time you use a concept from this course, you increase the range of problems that you can apply the concept to. How much can you expect your judgments, your decision making, and your problem solving to improve as a result of the concepts in this course? A lot. But there are two qualifications I want to make to that. One is, I make most of the errors talked about in this course frequently, I hate to tell you. And some of the errors I make constantly. The fundamental attribution error, it's several times a day, minimally, I'm sure, that I make the fundamental attribution error. So you're not going to be able to apply the concepts in this course for every circumstance in which they're appropriate, but you're better off for knowing the concepts because you're going to use them more often than you would have if you hadn't taken this course. The second qualification is that I'm just as interested in building up your humility as your confidence. There are just an awful lot of problems that we can't solve on our own. And for those, we're at the mercy of experts. I don't have a right to an opinion on whether vaccinations can cause autism, or whether humans are causing climate change, or whether vitamin C can prevent the common cold. Are the experts always right? No, for sure. I read the New York Times, and several times a month I see errors in it. It's the most respected paper in the U.S., but it's not got the straight boop on everything. Psychology errors are not that rare. Errors about social issues happen. Errors about health matters are not all that rare. So who are the experts you can trust? For politically relevant facts, there are websites like PolitiFact, which most people agree, whatever their political position, is doing its best to tell you what's truly the case about some matter. For health issues, there are websites like Cochrane Reviews, where you're going to do a lot better than just flying blind. And it's always a good idea, if there's an important matter, to check what your physician is recommending with Cochrane Reviews. And if it's different, find out why your physician feels differently about some matter. The mainstream media, in general, although they're much maligned, are relatively trustworthy, including, for sure, our two major national newspapers, the very liberal New York Times and the very conservative Wall Street Journal. The people who write the news for those newspapers and most other newspapers of any size, scale, or reputation, for them, telling the truth as best they can is built into their moral DNA. It's what they want to do for a living. It's what they feel they must do if they're going to be able to live with themselves. They're not infallible, these sources, but they're better than the alternatives, especially better than haphazardly discovered websites. You should think of the internet as a basket of candy, and a lot of that candy is poisoned. If someone tells you that the source of his information about something is the internet, tell him you think they're wrong because of something you saw scrawled on the sidewalk. And, of course, beware man-who statistics, whatever the source. Well, what you've learned in this course is probably going to be useful in your professional life. Even if you're young and haven't started a professional life. My daughter majored in art history. She now spends a lot of her time doing data analysis for a social media and branding firm. It's certainly going to be useful in your personal life. And it provides you with some protection against misinformation in the media. And the tools we've talked about are going to be more available to you a month from now than they are now. They're going to be more available to you a year from now than a month from now. Well, I'd like to invite your feedback on this course, ideas about how to make it better, because it's a work in progress. I'd like to know what you found useful and what you found less useful. I'd particularly like you to give me examples of errors you feel you're less likely to make now because of taking the course. And I'd like to invite questions about the content of the course. I'll do my best to respond. My email address is on the slide. Meanwhile, thanks for participating in this course.